Sur la configuration visuelle.
Il y a Aljosa qui m'a dit qu'il avait envoyé à. Ok, vous l'avez aussi. Bah, c'est bon, je prends le moment. Oui, j'ai reçu un email, moi. Je vais aller là. Hello, good morning.
Hi, Lara.
Hi.
Bonjour, bonjour. So, I think everybody's here. We can see everyone.
Je passe qu'on te laisse introduire en tant que président.
Hi. Quentin, everybody's here, everybody, yeah, face to face and remotely. So I will briefly introduce the committee. For this part of the introduction, I will switch to French so that all the audience can understand who are the people here. And apologize for the remote people who don't necessarily understand French, but most of you understand actually. Laura, I think you can speak French. Aljosa, I'm sure you speak a bit of French. Gabriel, I don't know. Maybe.
Well, you know, I used to speak some French years ago.
Yeah. So you should understand a bit. Okay. Alors, donc je suis le professeur Patrick Le Callet. Bonjour à tous. Et j'ai le privilège de présider ton jury de thèse, Quentin. Je te tutoie parce qu'on s'est déjà rencontrés. Et quand on s'est déjà rencontrés, j'ai eu du mal à rester dans le formalisme, même si aujourd'hui c'est un moment important et on va être formel sur l'exercice de présentation et l'exercice des questions-réponses. Donc, bon, je suis très honoré de présider ton jury. Donc moi, je suis professeur à Nantes Université. Je vais introduire donc les autres membres du jury. Donc, ton travail a été rapporté par 3 personnes, ce qui est rare, mais aussi je crois qu'il y a une histoire de label européen. Je viens chercher aussi au travers de cette thèse le label européen de doctorat. Je te félicite aussi pour ça. Déjà. Donc, alors, on a première personne qui a rapporté, c'est Madame Federica Battisti, donc, qui est associée professeure à l'Université de Padua, ici présent. Nous avons aussi donc Gabriel-Miro Muntean, qui est professeur à l'Université de la ville de Dublin. Alors là, je ne dois pas le dire, j'ai peur de décorcher le Dublin City University, donc qui est en ligne. Et donc, c'est le monsieur à la
perfect,
moustache.
thank you. That's the perfect name.
Nous avons aussi donc, le professeur d'université Gwendal alors, qui est professeur d'université, mais actuellement en détachement chez Synamedia.
C'est ça.
Et donc, oui. Professeur d'université, si je ne dis pas de bêtises, toujours à Télécom, comment on dit, Gwendal,
IMT Atlantique.
IMT Atlantique, l'IMT Atlantique, Institut Mines Télécom Atlantique. Donc, il y a aussi deux examinateurs. Donc, nous avons Toni, aussi en ligne, associée de professeur à l'University College de Londres, University College of London. Bonjour Laura. Et nous avons Aljosa Smolic, qui est professeur à la Haute École de Lucerne en Suisse, avec des belles guitares derrière. Voilà. Et donc, ce travail a été dirigé par professeur Lucile Sassatelli de l'Université Côte d'Azur. Et voilà, on en a fini donc, les introductions du jury. Donc maintenant, les 45 prochaines minutes, c'est toi qui parles.
Okay. So thank you, Patrick, for the introduction. Thank you everyone for being here. It's an honor for me to be defending my thesis in front of this committee. I'm going to talk about deep learning for adaptive streaming, adaptive 360-degree video streaming in virtual reality. I embarked on this journey in October 2020, and as Patrick said, I'm supervised by Professor Lucile Sassatelli. So virtual reality is a growing market with a worldwide market revenue expected to reach more than $30 billion by 2027, and has many applications on the horizon, such as entertainment, healthcare, education, corporate training, or also journalism. However, the limits of existing systems, such as imperfect hardware, network requirements, they impact the visual quality as well as the smoothness of the experience in virtual reality. We can cite, for example, resolution or artifacts that can affect the visual quality, or frame drops, stalls. And this can produce cyber sickness, lack of immersion, poor sense of presence. And in all of this, our objective will be to maximize the quality of experience. The quality of experience, it's a complex, multidimensional metric that is influenced by everything we just talked about. Everything we just talked about, visual quality, smoothness, cyber sickness, etc. It is fundamental to measure the perception users have of VR. We do not develop further this concept of quality of experience theory, but it's important to keep in mind that it is a driving factor in the optimization. So we are going to focus on the network requirements aspect, which impacts the visual quality and the smoothness. And to address this network requirement, I am going to introduce viewport adaptive streaming. So again, in the objective to maximize the QoE, what happened is that we have a person watching a VR video with a VR headset, and they can only see a portion of the frame. What we call the viewport, and the video. So we are talking about streaming, so it's streamed from a server over the internet, and it is stored in a tile-based representation or any other type of representation that can allow heterogeneous quality coding. And what happens with viewport adaptive streaming, the users send their head position, and in return, the server, they will send a viewport dependent content. That is, they adapt the quality to the viewport of the user, and so on and so forth, over the playback of the video. So the question we had with the viewport adaptive streaming is what to send in what quality. This is also a common question in traditional adaptive bitrate streaming, and this is the job of the adaptive bitrate algorithm, is to maximize this equation. This is the expectation of the quality of experience over all possible realizations of bandwidth, and over all the tiles in the frame and that appear in the viewport, and over a prediction horizon. So the prediction horizon, since we are going to focus on viewport prediction, predicting where the user is going to look, I'm going to explain this prediction horizon. So the server, since it needs to send, and there is some latency, so we need to predict before where the user is going to look. So let's say that we are at time t, and we are going to predict until the next positions of the user until time t plus h, possibly using a past history for the model of m seconds. So the prediction models, we can cite track, for example, a reference state-of-the-art model that uses both the past head positions as well as past representations of the past and future video content using an LSTM recurrent neural network, and it predicts a trajectory of future positions. We can also like another reference state-of-the-art, slightly more recent predictor, VPD360, which only uses the past head positions to predict the future positions, this time using a transformer-based deep learning model. So these models to one possible past, to one past trajectory, they will associate one future trajectory of head positions. And this association of one past to one future, it can lead to prediction failure, as we are about to see in this example. This is an example from a head motion traces dataset. So here we have an example where two users are watching the same video at the same time, and they have very similar past trajectories, user 20 and user 40. And we can see that they can have very similar past trajectories, they can have very different future trajectories. This user 20, they will go to the left, and this user 40, they will go completely to the right. So their future trajectories are radically different. And we confirm this by looking at not at just this one example, but at hundreds of pairs of close past trajectories in a head motion traces dataset. So here we see on 5 different videos, which are showed by the colors on the head motion traces dataset, the distance between pairs of past trajectories and the distance between pairs of future trajectories. And if the function that associates one past to one future, it was stable, we would see all the points, all the dots distributed along the y = x axis. And we can see that we have many examples of points that are above this line, which means that we can have a lot of cases of users with similar past trajectories, but different future trajectories. And this actually makes the movement quite unpredictable. So the question we ask, how can we handle this unpredictability of movement with VR? And to do that, we propose to design new models to predict multiple possible future trajectories of head motion, and not just one. And we also propose to study the factors that impact the unpredictability, such as emotions, in the objective to build new prediction models that will be informed by these emotions. These 2 axes, they will structure the presentation of today. So I'm first going to talk about the multiple trajectory prediction for viewport adaptive streaming, and I'm first going to introduce our contribution, which is the DVMS framework. So the proposition to predict multiple trajectories to account for this diversity, it was not done before for viewport adaptive streaming and for head motion prediction in VR, but it is something that is already quite common in a pedestrian trajectory prediction of one or multiple agents. We can say, for example, these models that from some years ago, and since then, this is the norm to predict multiple possible trajectories and not just one. This is also done in vehicle trajectory prediction in the self-driving domain. And for the contribution we are about to present, we worked with the authors of Mantra, which is a model using memory networks for vehicle trajectory prediction. And I spent 1 month in the University of Florence as part of the collaboration to develop with them the contribution I'm about to present. So the Bayes architecture we go from to predict multiple trajectories, a very classical recurrent neural network sequence-to-sequence encoder-decoder structure. So we simply input the past positions with this kind of model. It is encoded in an encoder of the past. We get an embedding of the past trajectory, and then this embedding is used by the decoder to decode the future head positions. We now introduce DVMS, our framework that we propose with the objective to predict multiple possible trajectories. So the core principle of DVMS is the introduction of this latent variable Z that is introduced between the encoder and the decoder, as shown here in the probabilistic graphical model, with deterministic states of the encoder and the decoder. And this latent random variable Z, it will introduce a perturbation of the past embedding in the latent space to express different modes of trajectories. And this is, as we say, a framework that can be actually adapted to any kind of sequence-to-sequence architecture. So how it works, these different values of Z. So we have our prediction model. It will take as input trajectory of the past head motion, our X, And for each different value of z, we will get a different predicted trajectory. So we have k different values for z, and this will give us k different trajectories, and each trajectory corresponds to a different mode of trajectory. Another important part of DBS, besides this latent variable z, is how we train the model, the loss function that we use during training. So usually what we do for deep learning models for regression, we optimize by minimizing the mean square error. But because in our case, we have multiple outputs for our model, we predict multiple trajectory, but there is only one ground truth trajectory that we can compare to. We cannot really use the mean square error because it would try to optimize all the values of z and all the trajectory to match all of the outputs. So it would not really specialize each trajectory. So instead, we use the variety loss that is actually also commenting in a pedestrian trajectory prediction. We can find it in a social GAN. And how it works, this variety loss for each. So we will predict all the possible trajectories with all our possible values for z. And we will compute the error for each of these trajectory. We will pick the trajectory with the lowest error, the trajectory that is closest to the ground truth, and we will only optimize the parameters of the model for the best trajectory every time we predict the trajectory. And this leaves the model free to explore the output space and really have different trajectories for different values of d. The implementation of the model that we propose. So here we see more in detail the architectural blocks that we use. So we use gated recurrent units, fully connected layers. So very simple network. It is very lightweight. It has only 110,000 parameters compared to the state of the art I was talking about of VPT 360, which has around 6 million parameters, and track, which has between 136 and 172 million parameters, depending on the type of saliency maps that they use. And Z is sampled from a one-dimensional uniform discrete distribution. So let's look at some trajectory that we predict with DBMS to get a better idea of the advantage of multiple trajectory prediction over single trajectory prediction. So here we come back to our example of earlier. We have two similar past trajectories for two different users watching the same video, and two very different true future trajectories. And here we can see what happens if we only predict one. If we only predict one, since we have a very close past, the model, it will predict two trajectories that are very similar, and it will not really account for the diversity of the two trajectories. But when we predict two trajectories, what happens is that the diversity of the outputs is really expressed in the model. And so here we have one trajectory that is predicted with one value of z, and another trajectory which is predicted by another value of z. And we can see that instead of predicting one trajectory that could maybe only fit one user, we can predict more trajectories that can fit more users. So here we have two trajectories that can fit each of them. So let's look at some quantitative results. So we tested our model on several data sets of the literature, so several head motion traces data set of people that have been watching 360-degree videos. Here we show results on the MM618 data set. So on the left, we first compare our model to single trajectory predictors. So what we show here is that we have equivalent performance to single trajectory predictors such as VPT 360 or deep position line that is very close to track, but only uses the head positions and not the video content. And we can see that when we predict more trajectories, the error of the best trajectory is lower. But since, so sorry, I didn't really explain. So here we see the prediction error of the model over the prediction horizon. So since we want to predict 5 seconds of future positions, this is the error at 1 second, 2 seconds, etc. So we see the prediction error over the prediction horizon. So against first single trajectory prediction, and then for multiple trajectory prediction, we compare to, since there is no previous existing model for multiple trajectory prediction of head motion in VR, we adapted from the self-driving domain, the Mentra, and we build the Mentra adapted baseline that uses memory networks. And we outperform this baseline by up to 41% on multiple trajectory prediction. So let's now go a little more into the latent space as well as the meaning of Z in depth. So we've seen that Z, this introduces a perturbation of the past embedding in the latent space to express different modes of trajectories. And here we show what the latent space looks like. So this is a 2D representation with a t-SNE of embeddings of the past that are learned by the model. So one point on this figure represents one embedding of the past, and the color here, we color the points by the speed of the past trajectory, and yellow means high-speed trajectory, and blue means a low-speed trajectory. And here we color them by direction of past trajectory. So red means that the trajectory is coming from the right, and blue the trajectory is coming from the left. And what we see is the distribution is not uniform. We can really see regions of high-speed trajectory, region of low-speed trajectory, regions of trajectories coming to the left and the right, etc. So this shows that the model identifies speed and direction as relevant features for the prediction. Now, if we want to know how does Z affect this affect the future by changing the representation of the latent space, we look at the distribution of the speed of predicted trajectories and the distribution of the direction of predicted trajectory for each value of Z. So here we have an example where we trained the model to predict 3 different trajectories with 3 different values of Z. And what we see here is one value of Z will be used to predict low speed trajectories with no specific direction. We see no peak here, while the others values for Z, so Z1 and Z3, they will predict higher speed trajectories with a specific direction. So we can see that the model, it learns to efficiently use different values of Z to predict different types of trajectory. It specializes them. And from this study of the latent space, we also derived some stationarity properties that enable likelihood estimation of each trajectory, which will be useful for the streaming optimization that I'm going to talk about just now, because now we are going to look how this multiple trajectory prediction can benefit an actual VR streaming system. So when we wanted to evaluate DBMS, we came to the conclusion that the existing tools to simulate viewport adaptive streaming were not really adapted to our objective. They either had unrealistic behavior. So what we mean by that is that they did not explicitly model the stall events. So when the video is rebuffering, it should stop the playback. And this was not really modeled, or sometimes it didn't have ABR planning, so adaptive bitrate planning for tiles don't only advance, or it lacked flexibility, it didn't support tile-based streaming, or sometimes only one type of tiling. So for all these reasons, we created a new simulation environment, which we name Smart 360. So this enables new large-scale evaluations for adaptive bitrate algorithms and viewport prediction algorithms, and we have made it available to the community. It is highly configurable in the sense that it is easy and fast to implement and compare new viewport prediction algorithms and adaptive bitrate algorithms. So we use this new simulator to evaluate the system gains of the VMS. And to do that, we have used 4 different data sets giving us 40 network traces and more than 3,000 head motion traces, totaling 132 users watching 94 videos. We use simple hybrid adaptive bitrate algorithm. So hybrid means that the adaptive bitrate algorithm will use both the estimated bandwidth and the buffer level to make the choice of the quality decisions. We have 5 different buffer settings, 7 different viewport prediction algorithms. So we compare DVMS predicting 1, 2, 3, 4, and 5 trajectories. We also use 2 different baselines, one that assumes that the person will not be moving, and one that we call no pred, so no prediction, that will give an equal probability to all the tiles. So this is a baseline, the most fair possible baseline, since it will not make any assumption. We have 12:6 video tiling to allow for sufficient resolution. 5 different quality levels that we encode the tiles in and that we can choose from. And this uses 1 second segments. So in total, we ran from these parameters almost 5 million simulations. And the metric I'm going to talk about now is the viewport quality. So the viewport quality is the average level of quality that is seen by the user in their viewport when we average the level of quality of all tiles inside the viewport, and we do this over time of all the playback of the simulation. So we look at the viewport quality gain over no-pred for both single trajectory prediction, so DVMS k equals 1, and multiple trajectory prediction, DVMS k equals 5. And here what we see is that predicting more trajectories leads to a slightly better average quality and a significantly higher median quality, which means that we had there was a quality improvement for more users and so yeah, this is what I just said, sorry. And the bottom figure here, we want to look at the prediction error for at the viewport quality for different levels of prediction error of the model. So we can see here, when we have bad predictions, predicting only one trajectory will be slightly better. But when we have high prediction error, we can see a 10% gain in visual quality for the 30% of users that will have a bad prediction error. And this really illustrates the trade-off that we have with a single versus multiple trajectory prediction. So predicting more trajectories will lead to a gain when we have users that are quite unpredictable, but predicting one trajectory will be better when we have users that are very predictable. But on average, for us, predicting multiple trajectory is still worth it because the average quality is slightly better and the median quality is a lot better. But if we want to do even better would be to be able to estimate the ideal number of trajectories to predict, not just 1 or 5, but estimate the ideal number of trajectories to predict. And here we can see that if we can indeed find the ideal number of trajectories to predict, the ideal k, the improvements are on average and median are much more significant. And here we can see again, when we look at the results of viewport quality against prediction error, we do not lose anymore when we are predictable. So we get the best of both worlds. This is good when we have good and bad predictability. But choosing this ideal k is equivalent to choosing the appropriate level of aggressiveness that we want. And this level of aggressiveness, it will depend on the predictability of the users, which depends on influencing the factors that influence the predictability. So this is what we are going to study now, the factors that influence the predictability of the users. So let's start with a simple graphical model of the VR experience. The immersive content that we are watching drives human attention and influences human behavior, but this can also trigger emotions that in turn will also affect the human behavior. And what we want to do is identify the factors that are specific to immersive content and emotions that affect the predictability of human motion in VR. So the question we ask, what are the influencing factors and how do they impact user motion predictability? To answer this question, we propose to create a new data set from VR user experiments with emotional data recordings. We propose then to investigate the effect of emotions on prediction models using this new data. First, looking at the effect of emotions on the accuracy of saliency estimators, type of prediction model. And we propose to look at the effect of emotions on the prediction error of deep prediction models as well. Finally, we will model the effect of emotions in the objective to build new models that will be informed by emotions. So first, I'm going to talk about this data set that we created. First, a little bit of background on emotions and about the metrics that we are about to use. So emotions, they can be represented on this circumplex model of effect that places on a 2-axis plane. The x-axis is the valence that can be seen as the positivity of emotions, and the y-axis is the arousal that can be seen as the intensity of emotions. And a common way to measure these emotions is the self-assessment mannequin when we ask users about their emotions on a scale of 1 to 9. So here we ask them about the valence, and here the arousal. Another way to measure emotions is to use physiological signals such as heart rate and electrodermal activity, which can be measured in real time with wearable devices. And the electrodermal activity has been shown to be a proxy for user arousal. So for the dataset that we collected, we had 31 participants watching 7 immersive 360-degree videos with a VR headset. We measured the head and eye movement in real time, as well as some emotion recordings. So we recorded the electrodermal activity and heart rate with the device that we just presented. And we also have valence and arousal self-reports after each video that the users have watched. And we also have made this dataset available to the community to enable these new kinds of analysis with motion and emotions. So now, using this data, we want to identify which factors really impact the predictability of the user. So in a first time, I will talk about these saliency estimators. So saliency estimators, they connect content and attention by estimating what area of the image or the video will attract the attention. And these estimations, they are called saliency maps. And in an effort to understand the link between content, attention, and emotions, we will look at the effects that emotions have on the accuracy of these saliency estimators. So with our new data, we will attempt to answer this question: how do emotions affect the accuracy of saliency estimators? So the saliency estimators that we are going to compare are 2 types of different saliency. So low-level saliency, which is related to pixel-level features such as edges, luminance, motion in the frame, and high-level saliency, which is related to higher-level semantic concepts such as objects, animals, and faces. So here we have an example where it was generated using a deep learning object detector. It recognized the elephant in the frame, and the video that we selected for our data set, they were chosen so that we can really compare the effect of emotions of both types of saliency, and that so to compare them, to be able to compare them, they need to be not always overlapping. So we have made sure of that. Now, to measure the accuracy of saliency maps, we use the normalized canvas saliency, very standard metric to measure the accuracy of saliency maps. It will compare the estimated attention with saliency maps to the actual fixations of the user. And the metric that we use, we aggregate this normalized canvas saliency, we aggregate fixations and saliency maps on 5-second segments, and we calculate the NSS, the accuracy of low-level saliency maps and the accuracy of high-level saliency maps for each 5-second segment. So now for the results, we look about this accuracy of high-level saliency maps against the user arousal for 2 different metrics. So the graded arousal that we had with self-reports, and this proxy for arousal, the centered SCR that is estimated from the electrodermal activity. And we look at the average of all users for each video. The colors, they correspond to videos of the dataset that we collected. And here we can see a trend that the accuracy of high-level saliency maps tends to increase when the arousal increases. And then when we look at the accuracy of low-level saliency maps against arousal, we do not really see any kind of trend or correlation. So this is what we observe. With this observation of accuracy of high-level saliency maps and arousal, we cannot claim causation. We don't know whether users will tend to focus more on objects because they are aroused, or maybe they are aroused because they focus more on objects. But what we can say is that this opens new lead for saliency models that depend on emotions and that would modulate the importance of objects based on the arousal of the user. Now we are going to get a deeper look at emotions and predictability by looking at the effect of emotions on the prediction error of deep prediction models. So here we have our usual prediction framework, where we use past positions and possibly video content to predict the future positions. And we say that emotions, they introduce some uncertainty in future positions, which may affect the prediction error of the model. So the question we want to answer is, how do emotions affect the error of deep prediction models? So specifically, what we want to know is which user and video properties affect the prediction error, and what are the relationships between them. So to answer this question, we are going to use two data sets. The one we just collected, PEM 360 I just described, that we created, and CAP 360 VR, which is another data set containing the same kind of data, containing user emotions and motion in VR, that was collected more or less at the same time in parallel. And in total, this gives us data for 63 different users watching 15 different videos. So since we want to measure the effect of some user and video properties on prediction error, we are going our outcome variable will be the prediction error of track, which is a reference model that uses both past positions and video content. The user properties that we are going to investigate are the valence, arousal, and the head speed of the users, and the video properties that we are going to look at are spatial information and temporal information. So quick background on spatial information and temporal information. The spatial information in a video indicates the amount of spatial detail. If we don't have a lot of detail, it's a low spatial information. If there is a lot of detail in the frame, it has spatial information. Same goes for temporal information, which indicates the amount of temporal changes in a video. So if it's a very static video, it will have low temporal information. But if we have a lot of moving things in the video, scene changes, we will have high temporal information. So if we come back to this question, which user and video properties affect the prediction error, and what are the relationships? The first observation that we made is that the prediction error tends to decrease when the arousal increases, and that the valence tends to increase when the prediction error tends to increase when the valence increases. Other observations that we made were that the head speed and the error were strongly correlated, and that we also observed a possible interaction between spatial information and arousal. So what this means is that depending on the spatial information in the video, the effect of arousal and prediction error might not be the same. I will come back on this when we model the effect of emotions. So to model the effect of emotions, we use a structural equation model, which is used to model the significant linear relationships between our variables. And we do this to quantify the effect of each variable on prediction error. The coefficients on the branch are standardized coefficients that indicate the effect size. And since this is only a way to model the linear relationships, we use a product. Here we have to multiply by the value of spatial information to model the effect of interaction that we saw just before. So I'm going to explain in detail this structural equation model. So to measure the total effect of valence on prediction error, we have to go through all the branches that go from valence to prediction error. So first, we have indirect effect that is mediated by head speed. So here, so this 0.19, what it means is that a change of one standard deviation in valence will cause a change of 19% of a standard deviation in head speed. And same goes here. A change of one standard deviation in head speed will cause a change of 85% of a standard deviation in prediction error. And we also, so to get the total effect, we also have to add the direct effect of valence on prediction error. And this is what it gives us. So the total effect of valence on prediction error is positive. It's 0.09. So it means that the valence tends to increase, same as what we observed when the prediction error tends to increase when the valence increases. And now, to measure the effect of arousal and prediction error, we again have to go through all the branches. So there is this direct effect of arousal, and then there is this effect that is moderated by spatial information. So we have to multiply by each possible value of spatial information. So when we have a low spatial information, we multiply this coefficient by -1. So what this gives us is that when we have a low spatial information, we have a negative effect of arousal and error. And when we have high spatial information, we multiply it by 1. So in the end, this gives us a positive effect of arousal and prediction error. So what this means, when we have a low spatial information in the frame, error will tend to decrease when the arousal increases. When we have a high spatial information, the error will tend to increase when the arousal increases. these important factors that we have seen, they motivate the creation of new prediction models that are informed by these factors. And this is what I'm going to talk about now. I'm now going to discuss ongoing work that we have to develop new prediction models that use this additional data, these additional modalities that are the emotions. So the objective of this work is to learn transferable cross-model representations. So this means learning representations from additional modalities such as emotions when we have them in training, but we don't necessarily have them when we test the model. So we want to learn representations that are transferable. This means that they can be learned when they're available in training, and still the representation would still be useful in testing when we don't have access to this modality anymore. This is inspired by recent work in vision language models. So these foundation vision language models, what they do is that they will train on both text and images, and then we can reuse the model or part of the model to work just on text or just on images, and they perform better than if they had not seen these two modalities. So we want to follow the same kind of idea. So with this diagram, we show the general idea, which is a modular deep architecture with encoders for each of the modalities, as well as a multimodal encoder. And the idea is that we can train jointly all this architecture with all the modalities, and then reuse it with less modalities, since it's a modular. The self-attention, so because we are inspired from these recent models, we also use transformer blocks, which are now the reference type of block that we use. And the problem with the transformers is that the self-attention, the core mechanism behind transformers, it scales quadratically with the size of the inputs, which can be problematic when we have a lot of tokens, which we can have when we use videos as input of the model. So for this reason, the design of the video encoder as well as the multimodal encoder follows perceiver, which means that we use a cross-attention mechanism of the input with a smaller latent query to project this input in a smaller latent space on which we can perform the usual transformer self-attention. So this really helps reducing the training and inference cost of the model while still having a good performance. So here we show some preliminary results of a model really to validate the architectural choices without emotions. So we compare the prediction error of our proposed model with state-of-the-art on 6 different data sets. We look at the prediction error, but we also look at the number of parameters of each model, which we consider to be an important metric for both practical and environmental reasons. It's better to have less parameters. And we can see here specifically, so when we use both fast positions and ground truth saliency maps, that we outperform the state-of-the-art quite significantly on all the data sets with around 150 times fewer parameters. So as I said, this is still a work in progress, actually in collaboration with CWI in the Netherlands, where I spent 3 months with them there. And future work include the integration of emotions in the model. So it's now time to conclude the presentation. So to the question, how can we handle the unpredictability of human head movements in VR? We say that we can mitigate the adverse effects of unpredictability by predicting multiple trajectories, and that we all have also shown that arousal and balance, they influence the predictability of head movements. So about this mitigation of adverse effect of unpredictability, we have designed a new state-of-the-art model for multiple trajectory prediction of head movements, created a new simulator to compare these prediction algorithms, and we have used this new simulator to show that multiple trajectory prediction improves fairness between users in VR. And in the second part, we have talked about the influencing factors of the predictability of head movements. So we have created a new data set to study the emotions and motion in VR and made it available to enable new kind new kinds of analysis, we have discovered a link between arousal and focus on high-level semantic concepts such as objects, animal faces using this new data. We have showed that arousal moderated by spatial information and valence mediated by head speed affect the predictability of head movements. And finally, we have started ongoing work on emotion-informed prediction model. So the next step that we see in this domain, we say that DVMS paves the way for multiple trajectory prediction in VR. So we can think of adaptations of DVMS for more than just viewport adaptive streaming, but for gaze prediction in VR, predicting the eye movements instead of the head movements. We can also think of predicting the movements of people in 6 degrees of freedom, in interactive environments. And we can also have models, content-informed prediction, such as track that uses saliency maps and not just past positions. And this kind of multiple trajectory prediction approach that is designed to handle the uncertainty, it also hints at VR streaming system that better consider this uncertainty of the movements instead of just the predictions. There is also exciting new work on the way for prediction models, including emotion-informed prediction models, as we discussed. And finally, we also anticipate foundation models to play an important role in trajectory prediction in the future. As we can see, that is right now revolutionizing the fields of computer vision or natural language processing, that we can really anticipate them to change things for trajectory prediction, which will certainly come with its own set of challenges. Thank you for your attention, and I hope you have many interesting questions.
Thank you very much.
Okay, thank you very much, Quentin, for this presentation. High speed.
Yeah, I should have.
Technical.
Yeah, I know.
That's okay.
I tried to
Really
slow down.
entertaining and exciting. So now it's time for the question. And so we'll start with the rapporteur. Because maybe, I don't know, Gabriel and Federica are used to this exercise in the French committee. So if you agree, I will give first the floor to Gwendal, which is very, I think, experienced in that part of the PhD defense in France. Just to remind everybody, so it's expected from everyone from the committee to provide some feedback about the work, feedback about this presentation, comment, and then, of course, questions. And we will go one by one. And no second round. Eventually, you can don't hesitate to go back. I want also to just remind to my colleagues who are attending remotely that we all see you anytime. Okay, so you are on the video that everybody in the audience can see you. Well, yes, Gwendal, please, the floor is yours.
Okay, thank you very much. So it's an honor to be the first one to ask questions as well. I really appreciated the manuscript, which is quite well written, very scientific process for the research with a lot of references. Any single question has been evaluated, explored, studied, and referenced. So it's an excellent scientific work, which is good. And the presentation was in the same vein, I would say, very dense, very rich. It is demanding for the audience people, and it's good because it's a PhD, so it's talking to the scientific community, talking to other experts. So it's a level which is very high, which is good. if you go into a professorship, you may need to go to be a little bit smoother in your presentations. But if for this kind of exercise, I think it's appropriate. I mean, some PhD students decide to, prefers pruning their work and selecting some chapters of their thesis for the presentation. You decided to go over all the materials, which is something, which is a choice to present how rich your research has been for the 3 years. So it's good. You are undoubtedly an expert in this area of studying very precise point of trajectory. I would not even go into details for this. Maybe the other rapporteur have a deeper knowledge on this deep learning, saliency, emotions stuff. So I would ask questions which are a little bit more general and maybe a bit challenging. So the first question I have is about the motivation for this kind of work. You did the bandwidth estimation is based on 4G networks. Now we have like a fiber everywhere, 5G networks. So this question of viewport adaptive streaming, first question, is it still something which is relevant in 2024? And for the next 3-4 years, is it something which we may have enough bandwidth for sending the whole video at full quality? Maybe, I don't know. So it's the first question. What is your opinion about it, and how do you?
Should I answer the first question first, and then you continue? It's easier for me if I answer the question, and then if you have a question, yeah, it's okay.
Yeah.
Okay, thank you. So first, thank you for the feedback. I'm very thankful for all the nice things you said. So about the relevance of viewport adaptive streaming in 2024, I think we can say multiple things. So first, I think it's always good to save bandwidth when we can save bandwidth. And also there is the bandwidth question, but also we're rendering on the side of the device. So if we send more, we have possibility to render more. And I mean, we can also get better devices, but then there are questions about the environmental impact of getting new and better devices that can really decode everything. I have, no, sorry, not this. I have something about the environmental impact. So it's really the manufacturing and the power consumption of the user equipment that has the largest environmental impact. So if we can put some load on the network to do some adaptive streaming instead of just getting better devices, it's better if we care about the environmental impact, which I think we do. And then the bitrate. I mean, now for traditional streaming, we can really have high quality with the networks we have right now. But for VR headset, we really need a very high resolution. Even the ones we have now, we are still increasing the resolution. So the bandwidth requirements are still very high. But maybe very far in the future, this will be less of a problem. But yeah.
I think it's a very good and very relevant reply. Indeed, so what you want to do is to prevent the waste of data transmission. Is it correct?
Yes. So we can see. I think we can see it in two ways. We can see it as for an equivalent quality, minimize the bandwidth consumption, or the framework that we chose instead was for an equivalent bandwidth, maximize the quality of experience.
Okay, good. So speaking of quality of experience, in the beginning of the thesis and the presentation, you talk about cyber sickness and other effects, and this is something which, yeah, the lack of immersion, the poor sense of presence. Is it something that you try to measure on your experiment during your experiments?
Not directly in our experiments. Something I didn't get into was that we also collected subjective feedback when we ran our experiments, not just the ratings of valence and arousal and physiological signals. We also collected something more in a free format where they could say whatever they wanted. So probably we can also find some information there about how they felt, if they were immersed or not, if they felt present. But we didn't have specific questionnaires about this, which I know exist. But this is not something we focused on.
And is it for, I mean, is it something that you want to explore in the future? Because I mean, what you said as a quality of experience looks more like a visual quality exclusively, and so it's could be related more to quality of service, as we used to say in the world.
So the definition for quality of experience, I mean, more like the metric that we use for quality of experience, was the one usually used, I think, in adaptive streaming in VR, which uses the visual quality. So the resolution, the variance, the spatial variance of quality and the temporal variance of quality, as well as the stalls and the rebufferings. But yeah, this is, as I said at the beginning, also the quality of experience is a very complex, multidimensional. So we kept it to a simple, measurable metric, but probably, yes, this would also be interesting to do experiments that are really designed to assess better the cyber sickness, the lack of immersions, and these components, because they are important part of the experience.
Yeah, I think, I mean, this concept of immersion is something that may require us going a little bit further than the just the visual impact that we in the video community have developed, which comes as well to something, because you went into the emotion analysis. Depending on the emotions, do people have different QoE targets?
Can you explain a bit more what you mean by this question? Or
yeah, so well, typically the lack of immersion. Maybe depending on the immersion we have, we don't have the same.
You mean the subjective perceived quality will not be the same depending on the emotions?
Correct.
This is very likely, but we did not. In our case, we did not measure this. But yeah, it would be interesting to look at this. This is not really something I worked on. I know that the people at CWI, where I was in Amsterdam for 3 months, they work a little more on this part with their experiments. They run a lot of experiments in VR. But in the experiment that we conducted and then the analysis, we did not really consider this.
Okay, and so you did not try to measure the immersion and the sense of presence?
Not directly, no.
Not directly, okay. So oh, it's a good for a more system point of view. I miss a kind of a view on the whole system. Where do you plan to implement this prediction module in the in the system, and how do you transmit the information if you need to transmit anything? Can you?
So I think there are several ways to do it. The thing that we assume in our simulations that this is done on the client side because we have the positions on the client side. So here, what we do is in our simulations is not, sorry, it's very if I use a pointer. Yeah, it's not exactly sending head positions, but setting a schedule. So sending really which tile do we want to download in which quality. In our simulations, this is what we do because the prediction is done on the client side. We could also, because here we only show one server and one client, but the network stack is obviously more complicated than this. Possibly there are like edge devices, CDNs. So I've seen some work that put this kind of computation load on edge devices. So I think this really depends on how much does the prediction cost and what makes more sense. I've seen also some recent work on federated learning. So this was done on edge devices. So yeah, so that's
so is
so the prediction that it can be done on server side, client side. It depends.
Okay. Yeah. But so the prediction, what you implemented is done at the client side, at the video player itself, or the HMI.
So our simulator, since it's a simulator, it's simplified version of the network. Yeah, this assumes that the prediction is done on the client side.
Okay, and so did you measure the computing requirements for this? Since
this is still theoretical work and not really the final product prediction model that we would use, this is probably not exactly the model that would run on a user device. But still, when we designed our model, we wanted to make sure that it was lightweight, that had a lot less parameters than other deep learning models. It also, something I don't show here, but that is in the manuscript, it has the lowest latency to predict one trajectory against its competitors. So yeah, and then when we have this kind of model, probably this can be optimized even more into a maybe even smaller model with there are techniques to prune and make deep learning models lighter without sacrificing too much performance. This is not the aspect we focused on, but we kept in mind during the design that we were not making a huge architecture that would not be realistic to run in a streaming context when we have to run it a lot in inference.
Yeah, because I mean, it would require some specific studies, I think, to understand where we should run this prediction and what is the impact on the delay if we run the prediction in the edge server, and what is the
impact? I remember approximately to predict one trajectory, it's in the order of milliseconds that we have, and in our simulations we don't run it all the time, but we only run it like once per second before requesting the tile. So this would add a little bit of latency. And this, knowing that this is not optimized for, the model is not in a optimized setting for streaming. So this could probably even take less time.
Okay. Another aspect which I'm not very familiar with, but it was a question I had, is about the personality of the people who tested the and you test. My understanding is that emotions is only one part of the personality of people, but we can have also traits, characters, and people who have more like who are more calm or more curious or more extrovert or more introvert? Is it something that you plan to study, or is it something which is in the state of the art not considered as a big factor? I mean, what's your opinion about it?
I think we can either look at the state or the, I mean, we can look at both, but there is the state and the profile. And we didn't really want to focus on user profiling because of the privacy concerns that this can have, really knowing and tracking how each user behaves by recording them, possibly then it will be stored on the servers and stuff like this. So the models and the study that we conduct are more designed to work in some sort of profile agnostic way. But this is definitely something we can use. For example, if you reported adaptive streaming, we place ourselves in the setting when we assume no previous data of people having watched the video. But if we consider these privacy concerns to be not that important, we can record we can record the traces of people having watched a given video, and this could also be used as an additional modality. And this is also what is already done in some systems. So this profiling, it's also in the same vein of recording and tracking things about people that we may or may not want to do, but we wanted to focus on more the predicting the state given the information that we have right now, and go from there.
Because the emotions for you it's a little bit less privacy.
If we run the model on the client side, then there is less problem of the data being sent to a server and then used to do the prediction and stuff like this. So if we consider it like this, I think so, yeah.
Yeah, but in that case, we could have personality. We could say, hey, I'm a curious extrovert guy. So
yes,
please.
it's true as well. Yeah. If you see like this, it's true. It's also true. Yeah.
And even
it's not something that we considered this profiling, but yeah, this is what is done also. I mean, I think this is the idea also with federated learning, having a personalized model for each person. So this is definitely something that is being investigated right now in other works, and probably deserves. Probably we could adapt multiple trajectory prediction in this context as well.
Okay. I have two other questions, Mr. President. Is it okay?
Go ahead, Gwendal.
First one is about gaming. My feeling is that the 360 HMD are used much more for gaming than for video streaming today. I believe your work can apply to the gaming environment as well. But there are many other inputs in the gaming world, not necessarily on the 6DOF, but on the action that you do in the game and on the intensity of the game and some other kind of aspect that are clearly related to gaming and not being a passive video consumer. So do you plan any work in this direction, and what would be your recommendations for further work in this direction?
So for gaming, are you talking specifically about streaming, or not even specifically in a streaming context?
Not necessarily in streaming context, but the same can apply, I think, meaning that
yeah, but in a streaming context,
stuff which is not viewed or not consumed anyway. So
yeah. So I mean, the work on trajectory prediction as well as the impact of influencing factors such as emotions that we did, some assumptions that we make, and the objectives of what we do are driven by the fact that we are considering viewport adaptive streaming. So so we don't predict the gaze, but the head motion, we consider horizons of a few seconds because we have the latency and the buffer of the network. So this will drive some decisions, and then the kind of model we are using could still be adapted to, yes, gaming, so either in a streaming or just the rendering part. So, but I think we would need to predict the head motion as well as the gaze, more importantly, which is even noisier data that is hard to predict, but that is also done in the literature. And we've talked about the additional modalities that we can use in a model. So you said not just the 6 degrees of freedom, but there are descriptions inside game maybe that we can use. So this could be used as an additional modality that we would use to make a prediction with a model. But again, we would have to keep in mind that we have to keep the model even more lightweight because the latencies in the gaming need to be even lower, unless otherwise the quality of experience would be really bad. So this is very challenging. And I mean, personally, I don't plan any work on this, as you were asking, but I think, yeah, there are a lot of things to consider, and this is complicated, but we can reuse some of the things that we did. This can be applied.
Okay, thank you. And so last question. So does it work in the end, the head prediction, viewport prediction? 2-3 years ago, I was in the impression that, I mean, it was a failure, meaning we were not able to actually predict the head trajectory, even if we did some papers about this. And so now, after your work, do you consider that this problem is almost solved, or are you still very far from it?
I think it's not solved.
Okay.
Because the movement is very unpredictable. As we said, this was the motivation for most of our work, that even with bigger and better models, we still have a lot of things that we can't predict. So we really wanted to accommodate this problem, that is a problem that the data can be too difficult to predict. So we can make the quality of experience better with what we described by, when we predict multiple trajectories, what we actually do is to spread the quality more. So when we have bad predictions, we will have less cases of, we have focused the quality at in one location, and we are not looking at this location, so the experience is really bad. So we have less of this. So we are doing better, but I think this is not solved. We probably need to continue to investigate the influencing factors, because what we did are studies when we do like the average on users and video, or the average on video, and we could do temporal studies, more fine-grained with more data. So I think if we want to continue to improve this, we need to study the influencing factors even more, and also design models that what we are doing right now that better consider these influencing factors.
Okay. Thank you very much. I'm done with the questions.
Thank you, Gwendal. So now we'll hand over. If you don't mind, Federica, we will continue with the online. So I will give the floor to Gabriel-Miro, Muntean. Gabriel, please.
Yes, thank you very much. Can you hear me well?
Yeah.
Excellent. First of all, many thanks for inviting me to assess the thesis of Quentin. When I read the thesis, I was very happy with its content, its presentation and structure. So many thanks for that. But now when I see the presentation, I'm even more happy. Now Quentin is also a charming kind of researcher, and your presentation has gone through the major aspects of your thesis in detail, and I'm very happy with that. Now, Considering this, I wanted to congratulate you first of all for the work, but now I have to kindly ask you to respond to some of my questions, if you don't mind. Is this okay? Okay.
Of course.
So first,
thank you.
So first of all, a generic kind of question, and so on. I see that you are very much concerned with the quality of experience and so on. And you have a slide there from the beginning, in which you put as with bold, the bottom, your goal to maximize quality of experience there. I have a problem with the word maximization there. So to me, maximization has to be proven, and so on. It means that no other solution can do better than yours, and so on there. I don't think this is the case for your solution. Can you elaborate on this, first of all? And then the second, again on the quality of experience, what can you say about quality of experience? Because I didn't see explicitly metrics, that would measure quality of experience in your thesis. So those two questions related to quality of experience.
Okay. So about so I think you were also talking about this equation, this one, where we say that our objective is to maximize the quality of experience. We do not claim to have an optimal way to solve this quality of experience, because in the end, what we say is that it's the objective of the adaptive bitrate algorithm to solve it, given what is maybe I have also another interesting slide on this. We have several approaches to solve this kind of quality of experience expectation to maximize the expectation. So we can so this thing about joint optimization or separate optimization. We could have framework where we have all of our data and we have the thing we are trying to maximize, and we could model it as a Markov decision process and solve it with the reinforcement learning as one joint problem, or consider it separately. So focus on the viewport prediction and the bandwidth prediction on one side, and then this would give us, for example, scores for each tile, and then this is the problem of we have. This is like a knapsack problem where we have a value for each tile and a cost in bandwidth, and the value is the quality of experience that we estimate from downloading this tile. I didn't detail too much the adaptive algorithm that we use for the simulations, but we use a greedy algorithm. So this is not necessarily optimal, but we are not really able to say what is actually optimal for the quality of experience. We since I'm trying to find the slide with yes, this one. So yeah, so no, we don't prove that the quality of experience is maximized, but we choose an approach that has this objective of maximizing the quality of experience, and we approximate it with our greedy adaptive bitrate algorithm. And then on the second part, yeah, sorry.
I think nobody else wanted to say something. No.
And the second question was about the quality of experience metrics.
Yeah, I think that's come to the point. That's the question. Yeah. What is quality? What is your QE?
So we, in the results that we show, we do not use directly a QoE metric. Here we focused on the viewport quality, that is the average level of quality inside the viewport. We do define quality of experience as a metric somewhere as a function of level of quality, number of rebufferings, temporal quality variance, and spatial quality variance. What I've seen done in many papers is that they have these 4 components, and they have a coefficient or a factor before each component. and they have to tune this as a hyperparameter. And we wanted to take a different approach and not be dependent on these hyperparameters. So the quality of experience that we define does not have these parameters. I don't have the equation with me right now, but it's in the thesis, and it considered these different aspects.
Yeah. So this is a key aspect, and so on there, how do you assess the quality of experience? Because obviously your model, focuses on that at the end of the day. So it's important for us to. Now, regarding the first question, when you mentioned about maximization, I would replace the word maximization with another word which is not as strong, and so on, I would say improving. Because you cannot, demonstrate the maximization or optimization using your technique. So my recommendation would have been for you to, consider, claiming an improvement of quality of experience rather than, maximizing it and so on, So in this regard, we are correct also mathematically and, scientifically and so on there, if you do not mind and so on, yeah. So this is my comment and so on. Now, the second, kind of set of questions and so on regards about the lower cost. You claim that you have lower cost than other, approach, but you never demonstrated this in your approach, and so on. You have only one claim that you use 110,000 parameters versus others that have much more than you and so on. However, the cost was never defined nor assessed in comparison with other ones and so on, whatever the cost means. So the first question, how would you define the cost and so on there? And then the second, how would you measure it and so on there?
Okay, so the cost here, we defined it as a computational cost of the model. So we talk about the number of parameters, but it's a lot lower. We also measured the latency of each model, how long it takes to make one prediction. And so having a lot less parameters makes also the training cost of the model much lower, as well as the inference cost much lower. We didn't define it here. I have some tables in the thesis showing the number of parameters for the model as well as the latency. Yes.
Yeah. So would you agree with me that this is an important kind of aspect and so on for bystander or for a person looking at the thing in order to analyze and so on there? Because obviously there is nothing like free lunch and so on there. So you achieve some benefits and so on there, but then you have to pay with something. The problem is, what do you pay and how much is that and so on there in comparison with others, so yeah. Okay. The third kind, okay, now I'm an engineer, so I go directly ABC and so on there. So, we go straight to the point and so on. Now, you talk about the best K when you compare your work with, considering one trajectory versus multiple trajectories. But you say best K, now, what is the best K? How would you define that? And so now, if you obviously you have the results, you can say, oh, this is the best one because, but if you don't have the results, what is the best K? Any trajectory could be the best, because I'm interested in something shiny in the picture and I look at the something shiny, no disregard to anybody's interest. Somebody looks at the skirt of a person in the, audience, much more interesting than at the ball in the, you know what I mean? So the issue is, and so on there, what is the best K and how would you define it?
So yeah, it's like you said, what is the best K? It's a very difficult problem. It's not something we can estimate, because if we could always, so here, but what we mean by the best K is not the best trajectory, but the best number of trajectories to predict. Because if we also were able to estimate which is the best trajectory all the time accurately, we wouldn't really need to do multiple trajectory prediction. We would always have the best trajectory. But here, predicting the best number of trajectories to predict, it's, as you said, something we measured by looking at the results. So of course, we are going to be able to know which K is the best. Here, it's important to note that it is not an upper bound. We could do even better because here we choose the best K for each simulation, but we can imagine that this could even be adapted over time if we are able to know, again, the ideal number of trajectories to predict, but this could be adapted over time based on influencing factors. So showing this ideal K, this ideal number of trajectories to predict, here we show results showing what would the results be if we're able to predict the ideal number of trajectories, but we are not, it's a difficult problem. We are not able to say which is the ideal K every time. And this is why we study the influencing factors to better understand what influences the unpredictability, and then this could be readapted to this multiple trajectory prediction model to estimate the best K. We chose to go back to model building to directly inform a model with emotions, but yes, this is a difficult problem, and this is why we want to study the influencing factors.
So actually, this could be part of the future work rather than a thesis outcome for your for this moment. Am I correct?
Yes.
Yeah. Okay. Now, because you're here, this slide and so on there, and I'll try to make myself the devil's advocate at the moment. And so on there. If you look at the results there, you have the average just slightly better than, you know, with a lot of effort. You know, you put a lot of effort to go from K1 to K5 and so on there, you know, and you have just a light. Now, your defense there was that, look, the median number is much better when you have a significant improved results, which, you know, is fine. But then what does it mean? It means that you improve slightly more guys there, but the improvement is minor there. Would they notice this? Is it worthy for you to have paid so much effort for a minimal improvement of, you know, yes, many, but minimal improvement that maybe is not even noticed and so on? What do you think?
So I agree with you. When we look on average, that this does not look like a big improvement. This is why we want to disaggregate for all users on the prediction error, that we really see that the larger improvement that will be noticed is for users that actually had the lowest quality of experience, and for them it's for them that we improve the most by predicting multiple trajectories, while we also lose a little for the users that had a really good predictability. So this is why on average it's very close, but that's why also we want to have this view on users to know who is going to have a better, in which case are we going to get an improvement, in which case we are not going to get an improvement. So here this is a quality gain of 10%, so I think this is noticeable. And the median, yes, this is to say that we have more improvement for more people, but this is really what's going to be noticed.
Yeah. Now, if you stand back and you want to deploy this, how would you think to be deployed? As a centralized approach or as a decentralized approach, considering these findings? Because you had an implementation yourself, which was, in my opinion, was centralized. Am I correct? And so on, if I understood well from your thing. But why I'm coming from this, you know, because these results tell me that maybe a distributed approach may help and so on there, you know, where, you know, the behavior may differ.
In the simulations, we assume that the prediction was done on the client side, but it's true that the model is trained once, and then everybody gets the same prediction model. So more decentralized approach, like federated learning, where we would have personalized models, would probably be a very interesting adaptation of this.
Yeah, because here, you know, when I looked at the results, I said, look, this is a great kind of example of where this would work, because there are some times where you don't need to do anything. You just don't do anything, you know. have a single kind of a K1 for fine, goodbye, that's it, you know. Only when it matters, then we do the distributed kind of approach way, you know, in my opinion. So, okay, thank you for that. Now I have another question regarding the content and so on. I don't want to take too much of your time and so on. You have not mentioned anywhere about the complexity analysis and so on. Now, I am a bit more mathematical in some aspects and very practical in others, but when I'm mathematical, I look at the measure of the complexity in terms of the big O kind of notation and so on. And I assess the benefit of my scheme and so on in terms of whether I could, you know, drop it, you know, from an n squared to an n log or to n whatever, you know. So I didn't see anything in your thesis now, any study about that and so on. So first of all, are you aware about that? And then the second, how would you apply this to, you know, machine learning? Because that's a little bit difficult.
Yes. Yeah, I think this is not always easy to apply this kind of algorithmic complexity measurements to deep learning models. I have not seen many papers that do it. I don't want to say, this is linear because I don't have any proof of this. So
I'm not saying that my question is easy, you know, so
no,
I just
no,
want to know it at you.
No, it would be interesting. I mean, we do measure more directly the latency of the model in time, more than proof of the algorithmic complexity. And since I think it would be interesting to have a study of the algorithmic complexity if we have variable sized inputs, because then we would know how this really scales if we have a lot of data or little data. But since we always have the same kind of input, which is the past head positions, which is always the same size, I think this would still be interesting, but probably not as useful as if we had a model that with a variable sized input.
Yeah, okay, thank you. I want you to think about it because this is an open kind of, how can I say, direction and so on, and you know, is very important. And now I have two questions at the end, which are more you know, generic and so on. So one of the, you know, I really appreciate your publications. I see that you publish a lot in MMCs. It's very difficult to go there and to get accepted, so congratulations for that. I noted you just have one journal paper published and so on there. Why only one journal? And, you know, who decides where to submit? Because mostly they are ACM publications that you have and so on there. So can I ask you, you know, how you end up with only one journal? And then the second, you know, what about the publication policy? And congratulations for the best paper award.
Thank you. So I think for the choice of venue to publish, I need to be very thankful to my supervisor, Lucile, because she really guided me with this on which conferences to publish, which journals. And then it really depended on what we had. And we had things that were really relevant for conferences or specific tracks of conferences. For the journal, maybe in some universities they will privilege journal publications and condition maybe the PhD on this. And here this is not the case. And even actually this conference article, the one that won the best paper award, it was longer than the journal article because it was 12 pages in double column. So this was even longer. So when we did the extension for the journal, we had to cut things from the article and obviously add new things, but we had to cut many things from the original article. So since they are also, most of them are six pages double column, so it's quite long. So it's not small articles. And the choice, why only one journal? We only had this opportunity for one journal. Maybe the ongoing work we have will lead to another journal article. Not sure yet, but yeah.
Because they're in general more appreciated for archival purposes, the journal papers and so on, you know, in my experience and so on. And also, as an alternative, I see that you have published in one IEEE conference, but mostly RACM and so on. And so I think that, you know, the type of work that you do, you know, can be equally considered for IEEE publications and so on. But anyway, the second question is regarding your, you know, what can I learn just myself or my own kind of, what do you want to do, an academic career or an industry kind of thing, if I may?
Oh, yeah.
Or if you can share with us.
So it's I do not have a fixed decision for what I want to do with my life after the PhD. What I want to do right now is explore options that I find exciting. So I'm in talks right now for a postdoc, so this would hint at a more academic career, but maybe after the postdoc, I will want to go do a more industry, private sector career. So I want to continue to do research and work on mostly the deep learning aspects that I am more interested in. But then I just want to do something exciting and meaningful.
Excellent.
Then,
good luck to you. All the best to you. And I'm going to hand over to the chair. So many thanks.
Okay. Thank you very much, Gabriel. You have the right to alternate in your career. I think you have a good example in your committee, Gwendal. I just want to, before to give the floor to Federica, remind that yes, we have a lot of ACM record track, only one IEEE, and we are not here to make advertisement for ACM or IEEE. This is not the question, but just to remind you that ICIP, for instance, which is a conference from IEEE SPS, Signal Processing Society, SPS is offering you the possibility to submit both in parallel journal and conference. And sometimes when you want to publish in a conference and you are kind of restricted by 4 pages or 5 pages and you want to tell more and so on, it's an exercise also to try to condense your work for the conference. And while you have already maybe 8 pages, 9 pages, 10 pages of material available, and it's perfectly fine in SPS to do the 2 submissions in parallel.
Okay.
Perfectly fine. There is no problem about that. And that's a scheme that I think a lot of the people are not necessarily aware of, and we should take advantage of it. And this could lead to maybe the conference paper is not accepted, while the journal it is, the other way around, and that's okay. And you should take advantage of that, especially because these things count also. And you should not miss any tribute to make your work visible, especially when it's a good piece of work. Anyway, sorry, I'm getting a bit, but I think that it's important also to convey that type of message. Well, Federica, the floor is yours.
So thank you very much for your presentation. I really enjoyed your manuscript and especially the topic that you're addressing that is very, very challenging. So you're putting together the problem of transmission together with the trajectory estimation and quality and emotions. So there's plenty of stuff and each of them is like a separate research field. So this was very challenging. So I have some questions here and there. And I also like your presentation because I think it summarized the big work because the manuscript is pretty rich. So it's, I think, the longest PhD thesis I read so far.
I'm sorry.
So there are always less than 200 pages. So
no, but there were a lot of references.
Yeah, that's true. That's it. So I like the summary that you did, trying to focus, you know, in these 45 minutes on the main aspects. I have some curiosities. Some of them have been already addressed by who preceded me. So I think the first is really linked to what Gabriel asked about the best K. So it was slide 18, and it's actually on the selection of Z. So basically, different Z lead to different trajectory predictions.
This one maybe? Oh, no.
Yes. Okay, no. Yeah, but here.
You said another number, 18. 18. Yes. Okay.
So you have different Z that reflect on different Ks. So you have different predictions, and then you compute the error between what you estimate and the ground truth. But as you increase the number of predicted trajectories, it's also kind of expected that you get closer to the ground truth. So how do you undo this in the end? So you choose the best K, and we know that this is already an issue there. So you end up with K trajectories. What are you going to do with that?
Yes. So actually, this was, I'm happy because I have some backup slides. It was left out of the presentation. But, so we have K trajectories. And even without trying to find the best K, using K different trajectories for viewport adaptive streaming, what do we do with this K trajectories? So let me find the slide. Yes. So we have this, and this is our objective. And the objective is to estimate the distribution. What is this? The distribution of viewport. So how do we go from multiple trajectories to a distribution? We associate a likelihood to each trajectory, which will in the end give us a viewport distribution from these trajectories. And how do we do this likelihood estimation? So we talked about the latent space, and here what we show is an example of the prediction error for trajectories predicted with different values of z. And here what we see is there is some stability in the error of a prediction for different values of z. That when we predict with z3, that it doesn't change all the time the best k, the best small k, not the best big k. So the best value of z does not change all the time. There is some stability, so we can use this stability in the error to estimate the likelihood. So each, so at time t, so at first, when we just start the video, we cannot do likelihood estimation at the very beginning, but then when we already have predicted some trajectories in the past, we can at time t plus r use this past error of each trajectory to estimate what is the most likely right now. And to evaluate this, if this was actually working right, we looked at the correlation between the error at time t and the correlation between the error at time t plus r. On several data sets. So here we have on the large, the CVP data set, we have a moderate correlation. And we also looked at this correlation for different types of videos. And here, so we follow a taxonomy that divides videos into a focus type, rides, exploration types, etc. And we see that for exploration types, exploration type videos that are much harder to predict, the likelihood estimation will not be as good as for ride and focus type videos that are clear points of interest. So this is what we do. We associate likelihoods to each trajectory, and in the end, we have this distribution that then we can use for streaming.
Okay. And can you go to the 57 slide? So now you're showing
Yes.
58 then.
Okay. Yeah.
So where you have the content, 59. I'm sorry, I didn't look into the number when you have the different types and focus and exploration. Okay, so those are videos, and how do you classify these? I think this is something I asked you to do in
Yes. So it's from the paper of Almquist, MMC's 2018, the prefetch aggressiveness trade-off. They talk about this. So the prefetch aggressiveness trade-off, they say that if we prefetch the tiles too early, then we don't have good prediction, so we will not have that good quality. But then if we don't do it early enough, there is the problem of the bandwidth instability that we will have a rebuffering also. So, and then they look at this trade-off for different types of videos, and this is where they define their taxonomy of, so as I said, ride type, so like a roller coaster type of video, focus type, they define static focus and moving focus. So static focus, there is a single object that doesn't move in the video. Moving focus, there is an object that is moving, but that is clearly attracting the attention. And exploration videos do not have any clear point of focus. Here, Porto, Riverside, and Plan Energy Biolab. Porto, Riverside, we are on the riverside in Porto, I guess, in the city, with the pedestrians, restaurants, many things to look at. And these different categories of videos, they lead to different behaviors, and possibly the results of the prediction models will be quite different for these types of videos, and also the type, maybe the video will be not as informative for exploration type videos, but it will be very informative for focus type videos and rights.
So now this goes to the data set you proposed. When you looked into the video properties, what you looked into is spatial information and temporal information. So these, we don't know the details of them, spatial and temporal of these guys, but what about your videos? Why you didn't account for the same?
That's a very good question. Yes. This one is hard to reply to.
Because the thing is, you are considering saliency, right? So saliency is basically telling where our attention is. So spatial information and temporal information are definitely great, features and cues that you're looking into. And this is I had another, so I have plenty of questions, but we can.
Do you want me to still represent? So
yes.
This the experiment that we conducted in the data set that we proposed, we had a few papers on the analysis that we did, and I think we can. This is also why it's made available to the community, so now everybody can do analysis, and probably it would be interesting also to look at the effects for different types of videos, because since the videos are also public, so we can see and attribute the categories to each of them. So this would probably be an interesting future work to look at these categories.
You want to say something?
Yeah, but yeah, I'm jumping in now because
yes,
for sake of efficiency. Yeah, because there are already existing open data sets that provide this saliency analysis, and you could say, okay, why not extending it for your work? And because you have already this characterization, and then so instead of doing the other way around, right? You have another one, and then now it's the rest of the communities that can do this saliency analysis, while you have already some data set that you know actually, and you have use, and you could have elaborate your selection of content based on the data set that provide already saliency information for 360. And I think this is how can we go beyond content?
But these data sets, we don't necessarily have the emotional data, and this is what we really wanted to focus on, the emotion part. So
of course, but then you can take instead of having SITI, you have also some content which are already characterized in terms of visual attention deployment.
Okay.
And you could
so it's about the choice of videos.
Yeah.
So the choice of videos. So about the choice of videos, we took them from a public database of videos that already had ratings of valence and arousal on average, and this is why we took it from them, because we chose them so that they had a wide range of valence and arousal. As well as this non-overlapping saliency that is not there, that is out here actually. So we choose it from this data set because we already had some information about emotions and motion in this database. So that's why we chose it from that.
Since we are here, so you use these 2D saliency methods for estimating saliency for solo level and high level saliency. And those are like well-established ones that are used. There are also, there are studies, and Patrick is involved in one of these, that state that the saliency and the exploration behavior for 360 is kind of different from what you have for 2D. So I understand you're doing this for viewport, on a viewport base, but have you, I don't know, consider like 360 prediction models? There are not too many, but
yes. So two things, I think. One, we did not directly apply models for 2D to the equirectangular frame because so here what we see is a projection of the 360-degree frame. It's the equirectangular projection, and what we did to calculate these types of saliencies, we did many smaller projection in 2D with a projection that makes it flat and not deformed, and we had 100 different overlapping patches. And we calculate this low-level and high-level saliency on each of these patches, and then we aggregate them back into the equirectangular frame so that the models that have been designed or trained on flat representations, they are still adapted, because if we run it directly on the frame, it would probably, especially the object detector, would probably not work really well on this. And secondly, about there are models, these are very simple saliency models. They are more advanced saliency estimators, deep learning saliency estimators for 360 images and videos. but we really wanted to focus on simple types of saliency that we can interpret more easily than a model that will say this will attract the attention, but it's harder than to do the analysis of why the effect has this, the emotions has this kind of effect or not. So, but probably it would be also interesting to add other types of saliencies and see maybe the weaknesses of this saliency. And strength as well.
Let me check. I'll make the selection. I don't want to steal too much time. So,
We are here for that. We are here for that.
And there is another thing. So this is, you're considering only exploration, basically. So you have a video. In your approach, in your work, what you're doing, you are looking at a video and that's it. So let's say the user is passive, is not really interacting. But you know, we're using VR to also to do things, and the task that you're doing is kind of important and relevant because this can drive saliency, for example, and you know, the things that you do where quickly you move. Have you considered this? I mean, if you can apply your model, or how can you extend your model in these cases in which you have an interaction and task to complete?
So yeah, in the data sets that we used to test our model, I don't think any task was given to the participant that explored the video. In the data set that we collected as well, we didn't give them any specific instruction. We told them that they were free to explore whatever they wanted in the frame. So the question is how we can adapt.
If you think it can be adapted, I mean, if you can somehow adapt your model and what you propose to an interactive environment. So go beyond simple exploration that is still interesting, but maybe now we're moving towards more interactive, multi-user, also some types of scenarios.
So I think if we could do multiple trajectory prediction for adapting multiple trajectory prediction for this, the influencing factors are probably, I mean, what we found is probably transferable to other contexts like these, but there are also other factors that we need to consider in this case. So this would require another full analysis of
maybe, you know, in the last part that you proposed, the one that you did in CWI can be this additional feature that you might want to consider. I know they're also working on multi-user systems, so it can be, I think, interesting.
Yes.
Maybe last thing, this is just something I wrote down. Emotions. So are they linked to the content? Did you explore this? It's balance and arousal, right? You evaluated balance, arousal, and then you had electrodermal activity and hearts.
Yes.
So electrodermal activity, you use some devices that are kind of invasive. So first, do you think this is affecting also the experience, since we are, you know, evaluating the quality of experiences? Is this?
I think for sure, watching the VR video with the VR headset, with the people around you and the device is not the same as watching at home. Probably the experience will not be the same, and there is some sort of bias that we could find in the data.
You didn't collect any like questionnaire in which you asked some feedback about the experience?
We did have a pre-questionnaire to ask how familiar they were with VR and this kind of usual questions. And we also had a questionnaire in the end really about how they felt, which was more free. So if they told us they were stressed out because of the context, we also wrote it down. But the analysis that we conducted, we did not normalize for these things. The thing we did for some sort of normalization, the metric that we use here, the centered SCR, it's actually something from the electrodermal activity that is pre-processed. And when this pre-processing, we get the skin consciousness response, and this is what is the proxy for also. And the normalization that we had was because the level is not the same for the base level is not the same for every person of the value of the signals. We could see it in real time that the values, sometimes the base value is 9 micro Siemens, and sometimes it's 1. So it's very different. So we did this thing of really looking at subtracting by the average for each user, the average value they had for all videos to really see the differences between videos more than just something that is specific to a user.
Now you said the magic word. I was missing one of the questions that I have in my mind since I read your manuscript. Metric. So quality metric. Let me find what is slide 23, 24. So you use this. I have it here in my. So this is the metric that you use. You said you don't have a slide for that.
Yes, right? The quality of experience. Yes.
So why did you use this one? I mean, why did you decide to assess the quality of experience with this and not, for example, resorting to some common state of the art?
I mean, to the best of my knowledge, when we were exploring the papers showing quality of experience for 360-degree videos, they had these usually these 4 components, which are quality level or resolution, rebuffering, and temporal and spatial quality variance. And they had these hyperparameters or factors in front of each of them. And this is something you have to tune and choose which one you consider important or not. And because we had this objective of measuring the fairness, in our case, we wanted to have a quality of experience metric that was bounded between 0 and 1. And like, I could not find one consensus on this is the quality of experience metric that we should use for 360-degree videos. Maybe I missed it. But we chose it because we wanted something bounded that takes into account these 4 factors and without having to tune or choose hyperparameters. But this is why also I focused on the viewport quality, which is a clear metric that is easy to understand the level of quality of the tiles that increases in the viewport, rather than focusing on our custom quality of experience metric that may be harder to grasp in terms of improvements, especially if we want to compare to the state of the art.
Okay. Thank you. Yeah, I'm done.
Okay.
Yeah. We can. I think we continue on this.
Okay. Okay.
We can do it later.
So okay. So we're gonna hand over to the examiners. So we will start with Laura, Toni. Laura, please. The floor is yours.
Yeah. Hi. Thanks. Thanks, Patrick. So well, I also echo everybody, Quentin, that it's very well done for the job, both in terms of content overall of what you did during the PhD, but also the presentation and the thesis that I think you could really see that is not just a copy and paste of the papers that you did, right? So even the fact that part of some publications were split and in different chapters or merged together shows that indeed you also put the effort in building the thesis. So I think that was very good. I also like a lot the fact that you have both learning, prediction, data analysis, but also data sets. So the breadth of the work, it's very wide. So well done in that. Some technical questions were already asked, so I go for more, let's say, philosophical and provocative one, hoping that you enjoyed the discussion. The first one is about the prediction. So you kind of want to tackle the aspect of unpredictability of the user, and you do it by predicting the user, right? So my question is, do you really, and it's also related to your comment of it's still an open problem in the answer to Gwendal question. So the first maybe high level question is, do you really think that indeed the trajectories of the user are predictable? Because even the fact that from a given path, you then can have quite diverse and different prediction. Does it mean that indeed they are unpredictable, so we should not go in this direction? or from what you did in these years, you think that it's challenging, but maybe looking at different parameters of modality or anything, there is a hope that indeed we can predict. So could you elaborate your insights on that?
Yes. So I think there is, even if we, I mean, what we are trying is to do better to better handle this unpredictability. And even doing this, yes, there is a limit to human motion predictability. I've seen that we can use metrics, not using directly a prediction model, but metrics about the trajectories of the users themselves to measure the unpredictability, for example, the entropy of the movements. And I think what they look at is how many parts of trajectory do not like repeat, I missed the right formulation, but there are metrics like entropy to measure directly with the information theory framework, the predictability of the trajectory. So I think there is a limit. We are trying to still improve what exists and focus on the problems of existing models and how we can improve. But yeah, in the end, there will always be a limit to the predictability.
But so I guess my question is also related to your solution on the multiple trajectories prediction, right? So I think somehow the foundation is that there are a lot of uncertainties, and you try to compensate with that with multiple cases, right? But do you think that the model generalizes well in this prediction, or is just kind of overfitting, but with 5 or k trajectories? So in the end, it works because it tries multiple options, but it is still more overfitting instead of actually learning something. So, or did you observe that in some settings you could see that indeed it was learning, and in the others, did you get any feeling on that from the study you did in the work?
Two things. Here we show results on a specific data set, and in the journal article extension, we show something when we train on one data set, the largest one, the CVPR 18, and the models tend to generalize quite well across other data sets. So this hints at something that this is not just overfitting, this transfers to other data sets. But also, I think that even what we do, multiple trajectory prediction, because the way we train it, it will really learn to spread the trajectories as more as possible. So the trajectory, they will not be perfectly following the user. We can see here it's way better than single trajectory prediction, but there is still potentially a lot of progress to make to really learn the trajectories even better. So I think this generalizes to some extent, and we can still do better.
Okay. Going to the slides you showed before, that I think it's the 19, right? I had a curiosity also from the thesis that is, so yeah, this one. Why do you have this trend that is a kind of up and down, so the not really monotonic behavior? So do you get an intuition on what happens there? Because it puzzles even when I read the thesis.
This is something we saw when we started predicting multiple trajectories. So this is most likely due to the fact that the trajectories that we predict, they spread very well in the different directions of space. And because the movements are very unpredictable, the trajectories, they are very noisy, the actual trajectories, but in the end, they end up going in one of the predicted directions. So I think that's why we see this, this goes down. But it would be interesting to look more at the trajectories and the prediction more in depth to really confirm this intuition.
Okay, but it's true, that makes sense. Okay, then maybe last curiosity about this aspect of this work, the DVMS. I would be really curious. I don't know if you look at that situations, like to understand. I guess what you get, right, is that for each zeta value that you get, you have some trajectories predicted. So for each zeta, you have a trajectory, right? And Have you observed some cases, just to understand better again the answer of generalization or not, if in some situation you get that multiple zeta tend to give the same or very similar trajectories, or in other content, they are very, very diverse. So did you see any difference that could kind of, lead you to also, if I had other 3 years, that could be interesting to be sought more or not?
I think with the number of trajectories that we predict, the models really learns to have different trajectories and to specialize them. But we also see some sort of saturation effect. So maybe if we continue to predict more trajectories, they will be redundant. And like the difference between 4 and 5 here, it's very small on this data set. So then the observation that we made of different speeds and directions, this example is a very graphical. We have some examples where it's harder to see. They always have different distributions, but sometimes they are closer, not that different. But then when we look at the trajectory, they are always different.
Okay, so you didn't see generative cases in which things were not that different or were very extreme that make you think, like maybe in some of these conditions. I guess my question is like
if we look for them, but we didn't really observe.
Okay, it was out of curiosity. Okay, it was out of curiosity to understand if you kind of understand the limitation of to which extent you can predict, basically. Okay, so then I'm very interested about the work of emotion. I really like that. I already wrote to Silvia the other day when we were reading. I was reading the thesis that. It's a very cool data set. I guess she knows already because you were there, but it's very interesting. So really well done. One question that is related again to Gwendal's about the sense of immersion. And maybe you know I work on more like similarity between trajectories that somehow they can be linked to a sense of immersion, right? The more they are synchronous, the more you can think that they are all engaged and they can feel a sense of immersion. Even if I know what you replied to Gwendal in the sense of you didn't look at that, like, did you see this aspect of similarities of the users in the emotions? Because you looked more at the correlation between these parameters, so prediction and correlation. But looking at the data, did you also observe any aspect of similarities, or did you get any intuition on that?
Not with our data. With DVMS for the likelihood estimation, we looked at the similarity between users for the error over the latent space. Yeah, with this kind. Yeah, I should have put another figure that's not there. But for the error of the trajectories, which Z will be better for which user. Yeah, this is not something included, but it would have been very interesting to include. We saw that in some videos, they always have the same Z that predicts them well, and some outlier users that have a different Z that predicts them well. But we didn't do this kind of analysis for the emotions.
Okay, I see. Okay, thanks. I think it's really, really, really interesting, the data set you provided. Then I guess going more toward the kind of conclusion, looking at questions on what would you do next, or what do you think could be useful. You mentioned it's also related about the representation and the multimodality. So 2 questions that you can answer separately or together. One is, which do you think are the key modality that we should include? Do you think there are other modality that we should include, right? Or other models, like you look at the prediction of human behavior point cloud, like, do you think we should encapsulate more information from any of this field, or more data, more modality? And the second is, should we look at the problem as generative model, or using maybe foundational model, like diffusion or other that you mentioned already, NLP? So what is your vision on that? Like, if you had to start the PhD today, what would you look, in which direction would you look in this perspective? Do you have already a clear view on that?
I would really intend to put everything on the on the table to think about where to go from. So about the modalities, I think, yes, it would be interesting to consider more, maybe even try to consider more past, because we have this, when we describe the prediction problem, we say that we take m past seconds, and this was defined as 1 second in the reference state of the art. When we also confirmed it, but then with our more recent models that try to use more modalities, we actually use a little bit more fast. We use 6 seconds instead of 1, probably using even more. If we have long videos, will be also interesting to really understand how the user behaves, and then the model would do the prediction based on the more information about the user. And then, yeah, if we can have information about emotions, it's better. But in our case, in our objective, we had the objectives to learn from these emotions, but probably they would not be available in testing. Maybe we can think, I mean, what we are doing right now is that can we actually learn, and before talking about, oh, we have them in train but not in test, can we actually learn something from emotions to improve the prediction? And this is what we are working on also right now, to just build a model that will benefit from the emotions without this problem of having them in training and not test as a first step. And then here we also have additional representation. So I think the more information about the content of the video would be interesting. So we talked about the video type of or category. We talked about the spatial information. And since we have seen that the spatial information may change the effect of arousal on the behavior, I think this would be also interesting to consider this in an ideal prediction model.
Okay.
Then there was the second question, maybe.
Yeah, it was like, is it worth looking at the problem? Is really like, if you have any intuition, or like, do you think it would be good to use any first more like diffusion models or any other type of?
I really don't know about this. I thought a little bit about this, about how diffusion model would look like for trajectory prediction, like denoising a trajectory iteratively. And I don't know if there is work on this already for trajectory prediction. I have not looked very recently. I was looking at the part on foundation models. I saw a very recent preprint, but didn't really go too much in depth on a foundation model for trajectory prediction. And there is also interesting work for time series forecasting with different kinds of models that try to adapt the transformer the same way we adapted the transformer for images with the patching. They adapt the transformer to time series with by patching the time series in different patches, and I think this is interesting. And probably I would try to go in that direction if I had to start again.
Okay, thanks. That's let me see. No, okay, these were all my questions. Congratulations again on my side, and I also would like to remark that indeed I also think that MMC's paper are very, very long, so they're not journal, but the count as. So there will be the idea to do what also Patrick said about the SPS. So indeed, I think you did very strong. I mean, you have a very strong output. So I just wanted to stress again, I didn't do it during the feedbacks. But thanks again.
Thank you.
Thank you, Laura. Now over to Aljosa Smolic. Aljosa, please.
Yes, hello everyone. Yeah, no, I to catch up on that one, I also feel that in some communities the conferences are even more higher regarded than the journals. So and that's probably the case. And ACM is also a very reputable association for publishing. No, but thanks a lot. I really appreciated learning about your work from your text and from your presentation, and also from this very animated discussion that you already had with the other examiners and rapporteurs. So there's not much really left for me to say at this point. I think you demonstrated in all these different disciplines your ability to be an independent researcher and find solutions to relevant problems, which is kind of the definition of what it makes to become a PhD. So I'm quite optimistic about that already, but I have a few thoughts, maybe more thoughts and questions. For instance, in your objectives, you write about predicting the viewport in VR. Are you actually doing that in your work?
So yeah, let's put this slide. So what we do is to predict the center of the viewport, and then we assume a fixed field of view with a fixed shape. So what I've seen in viewport prediction for VR, I've seen mostly two kinds of work. The ones that predict directly the probabilities of each tile, and sometimes they formulate this as a classification problem for each tile, and the ones that do this in a trajectory-based manner of the head motion. And the trajectory of the head motion, it gives us the center of the viewport, and in the end, this is how we get the viewport, and we chose to go on the trajectory prediction side of things.
Yeah, no, because a viewport in VR is a Sixtov thing, right? So it depends on motion and rotation. And you also talk about trajectory. So it can be, you can think about a 3D trajectory or a 2D trajectory in a spherical image space. So these are all a little bit different things, and you have head rotation versus that. So I'm just saying that in some places, maybe your formulation should be a bit more accurate, so that you don't say VR, but 360 video prediction in that sense. No, but otherwise,
I should have been more precise. I should have been more precise that, yeah, this is 3 degrees of freedom, the trajectories of the head orientation, and 360-degree video, not yes.
But it especially struck me as it's very prominently in the objectives, and maybe that's a point where it should be very crystal clear. But just a detail, very picky one, so sorry. Maybe another detail, I know, maybe slide 14, there you introduce this variable Z, which is... So can you talk a bit about the intuition behind that? So is it a kind of random variable that kind of steers the process into different directions? And so you sample from random distribution?
So here we have our encoder and decoder, and these are deterministic. And we say that Z introduces a perturbation of the past embedding in the latent space to express different modes of future trajectories that will be decoded into future into different future trajectories. This is a discrete variable, which means that this is not sampled from a continuous distribution, but from rather a discrete distribution. So these are fixed values that we can reuse, and that's why we can do the likelihood estimation, because we can reuse the same values for Z. And we did that on one hand for because of the likelihood estimation, it's much easier like this, and also because having k different fixed values for Z was actually led to better prediction results than having continuous normal Gaussian distribution that we would sample from, for example.
Okay, now I get some of the discussion earlier also. So you have k predefined values, and you sample from these k values, not from a distribution. Okay. And then maybe if you go to slide 37, that's a few things. So I also like this concept of thinking of emotions, and how do emotions influence the behavior, and how does that influence the saliency. But honestly, I found it a bit vague and a bit, I mean, the size of the data and all of this is maybe not big enough to make too strong claims about that, right? But so here, for instance, you say there is this connection between arousal and content, which is something interesting to know, obviously, especially also for content creators or filmmakers because it means that if the content is engaging, then also the attention is following if the content is engaging, and if the content is maybe less engaging, then it tends to be more random and people may look around more. Is that an interpretation that is reasonable from your claims?
Sorry, can you repeat the last part, because I was thinking about the first part of the questions. I'm sorry.
No, well, I feel that you make this connection between arousal and predictability, right? So the more engaging, the more predictable.
Yes. So in the slides, we say that I said that we cannot claim causality, and about the weakness of the results, I agree that we have 7 points on the plot, so that's why I didn't draw a regression line, because we don't do regression on 7 points. But this is the average for each video, and we actually have an analysis where we look at the average for each pair of user videos when we have a lot more samples, and we have a moderate correlation between again. So mentioned that I didn't introduce during the presentation, but the NSSDIF is the difference in accuracy between the 2 types of saliency maps. And this is what we observed for pairs of user videos. I chose to show the results for the average on videos, but we also have this analysis that is, let's say, statistically stronger.
Mm-hmm. Yes, I agree. I agree that it's a very interesting thought and a very good start into what is a big topic, and so there could be a lot of more evaluated along these lines. That's what I would see here. And also the question that was discussed earlier, it obviously depends a lot on the content that you showed and the videos that were selected. So what was there in these videos? Was there any story? How long were they? And all of this obviously contributes to this kind of attachment and correlation in the end, right? So was it kind of cinematic content where there was a story? Was it kind of some people in action? Was it just random? All of this would strongly influence these kind of emotional attachments and connections, I would assume, right?
Yes, I think there will definitely be a bias in the data with confounding factors for each video that we do not account for here. That's why it would be interesting to, that's why in the second analysis we do use data from 2 data sets to have more data for this kind of confounding factors to have less impact. But the videos that we used, they were played without sounds, so that the narrative components were less influencing and more the saliency of the objects and the low-level saliency and things like this. But then, of course, there is also going to be a different experience for each person. There were, I remember, during the experiment, some people were. There is one video about animals in the nature, and some part of the video is underwater, and people were afraid of being underwater and afraid of marine animals. So, of course, this will play a role, and this can have an influence. That's why we try to collect as much data as we can to the effects.
But to the point, right? So you made you presented a first attempt towards an idea which is really wide. So you could do thousands of different studies with different videos, different conditions, audio or not, and all of this. And I'm sure others will probably catch up on that. But that's a good thing, because as a PhD, if you raise a new question, that's also a very, very good thing. And if you make a contribution. As a last thought, maybe, so these 2 parts of your thesis are very valuable and strong, but they are also a little bit disconnected, right? So they are in different areas. So one is more looking at this saliency and emotions, and the other some classical streaming. So can you talk a bit about how was the timeline? Did you do both of them in parallel, or did you do once and then the other?
So very straightforward answer. we started working on the prediction models. We wanted to improve the existing prediction models. We saw that there was this problem of predictability, a lot of overfitting in the models we were trying to do. So we then started to try to better understand this unpredictability, first with other approaches, trying to quantify the uncertainty. Where's the slide? Yes. We characterized the uncertainty. It can be characterized in two types, and we had a first approach where we use a kind of model that will explicitly give us metrics about the uncertainty of the predictions. So we were working on this on one side. Then there was actually an existing project about user experiments to measure the emotions of people in VR. So I worked on that in parallel actually, but then it links. I think it links very well because it's really always about this unpredictability of the movements. And on one side, trying to how can we do it on the model side to improve, and then how can we understand it better? And again, in the end, in the objective to improve the prediction in the end. So this part was done in parallel. Then we came back on the prediction models. We came up with the DVMS, and then work on the simulation aspect, which was quite complicated. It took a lot of time, and then trying to use all of this, the emotion part, the prediction part, to build new models that use the emotions at the end, and it's still in progress.
Yeah, interesting, because in the end you get this text and you get this end-to-end presentation, which is kind of following a logical red thread, but often the trajectory of such research is highly non-linear. So good.
Yeah, that's sometime in my PhD it was hard for me to really see. I was a bit lost. Now it's clear because it's. I mean, how to say? Thankfully, it's clear. It's good because I am defending, so it's good that it's clear in my head. But at some point, yeah, it was a bit. It was hard for me to make all the connections.
It's good to see, and I think you did a great job with that. And I think that's it from my side. Thank you.
Thank you very much, Aljosa.
Thank you.
We'll hand over to myself and before to give the. If you agree. Sure. I really like actually your last answer to Aljosa uncertainty, because to me it was, you made this link actually during the presentation. It was an uncertainty is really the word that I wanted to point. We'll come back on that if you have still some energy. You have still.
We can. I can find it.
Okay. So let's just first concur with my colleagues. But I find your work very inspiring. Maybe they don't say that, but some of the stuff that you are doing are really inspiring, and because I think you have to acknowledge that you have this talent to bring all these things, which is these days in computer vision, AI, and this type of thing, which is somehow give the feeling that it's a bit incremental, but you borrow all these things, try to bring important applied topic, but trying to give a sense of this, right? And why you are choosing this, and so you are really doing this connection between the domain, and you do it with in a convincing manner. So that's many thanks for that. Sure. And also because you have this also say curiosity, okay, and it's pretty obvious that the presentations from the manuscript you embrace topics and you want to make things. And if I read this stuff, serment doctoral d'intégrité scientifique, whatever is going to happen in the next minutes, if you get your PhD degree, and if you want to tell it, at least the very first part of this script is about what you have done. And there is an important thing, quest for knowledge, which is mentioned in this sermon. Carry on demanding research, demonstrating intellectual rigor, respect of the principle of research integrity. And when I read these things in the assignment, I think you should work perfectly. So congrats for that also. Another thing that I want to point out, because it was not necessarily coined, is that the paying attention for reproducibility. Now, all this ACM stamp, and that's the value also of ACM that really encourage that, and the fact that you have pay attention to that, I think it's also something that we have to acknowledge here, and congrats also for this. Even if, yes, we should sometimes, as we have discussed about data set, make better connection between the data set, because at the end of the day, we may have a lot of, everybody has these stamps, but how we elaborate knowledge all together, that I think that I wish we could see a little bit more. Also the community, so it's not only your responsibility, but thanks also to maybe to come back on the sequence of this work. The thing also, the second work requires, second part of your PhD requires also some subjective experiment, which is not necessarily the things that you need for the very first part, because you can rely on many other things. And I think we should not forget that if I look at the date of your PhD, you are coming from a COVID-19 PhD student hurt by that, and actually cannot feel it today. I forgot that, right? And this may explain also, I don't know, you can answer to that, but maybe for the second part, you need to do experiment with people and so on, and this was not possible probably at the beginning of the PhD.
So, later,
yeah, you can, please.
I'm thankful I started my PhD actually at the end of 2020, so it was not the big wave that the PhD students before me had.
Yeah.
Like me, there was one lockdown where I had to work from home, and then when we ran the experiments, there was still some protocol of like they had to wear the headset, they also had to wear a mask, they also had to wash their hands. I mean, it's always good to wash hands anyway, but yes, this was also additional stress on the users of the experiment. But yeah, I don't think it was impacted too much. It impacted a little, but
yeah, but it also makes you apply some constraints that you don't think that you should embrace that topic. You say, oh, it's more. We know that running this experiment is already costly, time-consuming. And everything in the lab, and in that condition, it's another order. But that's okay. Let's not spend too much time on this. I'm really glad also about the answer you gave to Gabriel about what you want to do after. And I think that's a good choice when you say AI, because you have this talent to understand what's going on there. But it's also meaningful, and that's important. Meaningful. We'll come back on that. And so, you know, you have to decode also my latent space. So when I'm going to ask you a question, it's always a bit difficult. So good luck with that, to decode my latent space. But since you have this talent to understand what's going on in AI, let's see how it goes there. Just so, I want to discuss with you uncertainty, sustainability / transferability, and ethics.
Oh,
okay. But as a warm-up, sciency, quality, emotion, slide 35, please. Just a warm-up, and it's easy. Of course, it's extremely frustrating, this part for me, because I use a low level, high level. You know, I'm working in sciency for quite a long time, so I wish I could see top-down, bottom-up, overt, covert, explorative versus focus. And we know we have a lot of models, so we can characterize the content. We have a lot of models that can also predict this type of things. Is it more focus, exploratory model? And you didn't use that, so that was extremely frustrating, because you could have taken this part of the existing work to characterize your content, design a more meaningful maybe data set. So a bit of frustration, but that's okay. That's okay, because you have already a good in-depth knowledge of big pieces of state of the art, and you cannot embrace everything.
This is also what is hard when we have so many components. We cannot be a specialist.
But there is Can you show? It's maybe one slide after when you have this.
Normalized scan perception.
Voilà. Just a simple question. Why 5 seconds?
Why not?
No.
So we wanted to have enough fixation. So we didn't do the whole video because if we do the whole video, it doesn't really match because there is this temporal aspect of we are looking at this at sometimes. But why 5 seconds and not 1 second? I don't have a definitive answer to this question. We chose it because it felt good for the analysis. If we don't have enough seconds, then there may be some latency effect, like we don't immediately look. So we wanted to have enough range.
What is the duration of the fixation?
It depends.
In average?
I don't know. Milliseconds?
Yeah.
Or seconds?
How many fixation per second?
I don't know.
You know, that's but typically this type of knowledge, this is what you could bring to justify this 5 seconds. And that's okay if you don't know, because you cannot know everything, right? You know things that I don't know myself on computer games, that's okay. But this is, you know, this type of things like Wi-Fi, one point of time, I want to. So understand from, especially now we are touching human factors, emotion, science, and so on. We need to also take some of the knowledge that is coming from psychophysics, psychological studies, all these fields, and then maybe it helps us to design better algorithms at one point of time. Just to make you aware of that. But that's okay. And I just want also to just tell that there has been a lot of study on 360, saliency, quality, emotion already, at least for still image, a bit on video. And it would have been nice also to make this connection with your study, what we learn, is it in line, not in line, what we work in addition, but you can. I'm very pleased that you mentioned audio. Yeah. You mentioned with, I wish I said, okay, there was no sound. And that's, I think, very important for the emotional part, especially. So it's a bit weird to me that we do this type of study just using the visual stimuli, while when we are talking about QE, everything comes and once again, for quality, this has been already kind of, even for 360, when you want to allocate your quality on audio, image, video, you see, it's always the visual stimuli that is more consuming, and this is where you should put the quality overall. But I think that for science and for emotional part, this is different. And audio is conveying much more information. Any thought about that? You have some evidence papers that...
I know that Aljosa and his former students, and maybe even current students, I don't know, have been working on audio visual science for VR.
But for the emotion also, do not forget the emotion.
For the emotions, I'm not sure.
Yeah.
But I mean, things are. No, I know the state of the art from 2022.
But where I want to drive the discussion, and it's also a bit in line with the discussion of that Gabriel put on. You may look for some marginal improvement with your techniques, because maybe you are putting the context of the experiment where there is nothing much to get in. You can just have an incremental result. Well, if you put the things in perspective and say, okay, maybe uncertainty, emotion, science, and audio play a role. And this is a strong choice to say, okay, I'm going to play this without sound. While maybe for the effects that you want to measure, the effect of emotion and on attention deployment, and the audio part is maybe...
I think it plays an important role. I think this will not be a good answer, but there were also practical considerations. And I think the headset that we used didn't really have a good audio setup. I mean, this is not a good justification. You just get
audio quality, right? It just how the audio play a role in.
But if we had done it with audio, I think the audio would have come from the TV and it would have been terrible.
Okay.
But
There are
yeah.
papers also that demonstrate the quality of audio setup in terms of number of speakers or only binaural or just you have I would say a bunch of literature on that. But maybe looking at that would have helped you to study a more promising scenario. This is one where you can better demonstrate the value of it. Okay, alors uncertainties. So I'm sorry, Quentin, but I'm still not yet satisfied with the slide 24. We are going back once again during this session. Yeah, this one. Okay, and this has been touched by most of us. What is quality here? The measurement of quality. What it is in this figure?
Which
report
one?
quality, I understand, but
Okay.
what is exactly the? How do you measure this?
This number?
Yeah.
So here we have the simulations. We have 5 different quality levels, and each.
Is it subjective quality? Is it VMAF? Is it PSNR? Is it SSIM? Is
Yeah,
it,
I'm going to tell. It's CRF, the constant rate factor for encoding. So because I've seen most of the papers
CRF.
they do CQP, and so it's not directly the CRF. It's the level of quality. For 1 is the lowest and 5 is the highest. So 1, 2, 3, 4, 5. We have 5 levels of quality, and each level of quality corresponds to a CRF. I didn't put the exact CRF
but
here,
it's okay. So it's a coding parameter translated on a quality scale.
Yeah.
Okay. Okay. So here with this work, this particular work, right? You have 2 levels of uncertainties. One which is the behavior between users. So the possible trajectory, multiple trajectories that may happen. Okay. We discuss about that, and that leads to this K, and you are playing around. And there is another level of uncertainty, is I trust this number, this quality number, especially when you have 10% of gain. Quick question, is it this 10% of gain subjectively, statistically significant?
It's very hard to say because these are simulations, though we don't have users to tell us this is significant or not. So
but when we have, these days, when people use metrics, like whatever, you could have selected SSIM, VMAF, and so on. People try to characterize the uncertainty of these metrics. So means that you have a quality metric, you get a number, but you said, okay, based on this number, there is some kind of margin, confidence interval, in which when you vary this number, you cannot say that there is really a difference. So you see what I mean?
Yes, maybe the word quality is not well chosen for this. It's more like the encoding level that we are able to transmit would be maybe a better choice than say quality, because then you think about the subjective quality, which may or may not be as significant.
But it's still what you are using. So suppose this 10% of gain is not really visible, noticeable. Is it worth the effort?
Maybe not. Maybe, I mean, if 10% gain is not noticeable, I don't know if it's in this case worth the effort to do even a deep learning prediction model, because we don't show it here, but when we do the static prediction, where we assume that the people do not move at all, it's already a very strong baseline in prediction and a very strong baseline in viewport quality. The results are also quite close. So depends on how significant the.
No, but where I want to grab the discussion, as an engineer, we love numbers. Okay, we need numbers. We need something that quantifies the stuff. But do not forget that even as engineers, when you have a measurement instrument, you are interested by its accuracy, its precision, and all these things, right? And any number you're gonna get with your probe and your instrument, you should always interpret it with respect to its accuracy and precision. And that's what I'm inviting you to consider that for that particular result.
Yeah,
I tell you, for quality these days, even if you have some things like, so you selected the CRF as a proxy for quality, and that's, but how did you qualify this metrics in terms of accuracy to predict the real gain from the end user? You say, okay, I'm improving fairness between users. Fairness in which sense? This is a strong statement.
Yeah, so fairness here in the sense that we have less difference between users.
Are you sure about that?
In terms of, so I don't know in terms of quality of experience. I mean, we also measured quality of experience. We have it in the other figure in the thesis with the definition of the metric of the quality of experience that we chose. And the gain is 5% if we take into account the stalls and the temporal and spatial quality variance, because we are usually improving the quality here. It also tends to increase the variance in quality as well.
I think, once again, my message is that be careful, because you may deploy some stuff which are not necessarily very useful.
But I think this kind of simulation is the first step. Like first is the prediction, then we have this kind of simulation that is cheap compared to testing it on users, and then a next step to know if we actually have gains would be emulation or user experiments.
We know that, for instance, for quality of the viewport, we have perceptual metrics which are existing, that have been validated on subjective experiments. They are kind of well correlated somehow, and there is these days a trend to also qualify the confidence that we can have in these metrics. For instance, if you take VMAF, it is well known that for a certain quality range, the difference of VMAF of so it's on a scale of 100, if I'm not mistaken, then difference of 3 or 4 of this number is not meaningful subjectively speaking. So it's about the metric. I don't know, there are many ways to call it, resolution power, confidence. So just take this. It has been done by the community of quality. They have validated the stuff, you know this, and then just ingest that.
Yeah, it's just that I think this kind of metric, it is possible because first, the simulator is open source, it's available, so we could implement new metrics. And also this would probably cost a lot more than just looking at the level of quality of the tiles that were transmitted, because I assume that we have to, for VMAF, for example, we have to get the frame and calculate from the frame the VMAF, right?
But you get your viewport quality. Yeah, of course, you have to do it with in the.
I mean,
it's not only just based on the.
Here we can just look at the logs at what was transmitted and directly.
You want to do that in a parametric model. So you are using parametric model of QE. Okay, parametric model of QE. There is standard ITU standard that define. You have different profile depending on how you exploit the bitstream parameters and so on, and that have been qualified. So you don't hesitate to do that. Not necessarily 4016. That's why it's interesting to look a little bit into that. But I think the way you propose to do that, which is the viewport quality, is a way to go. And then you can easily use ITU standard. And ITU standard, do not forget, it's a result also. This is reproducibility also, right? Because it's a result of people who put effort together and try to find out the model. There are different levels of model, depending on how you get access to the bitstream. So some are just using SITI, CRF. Some are going a little bit deeper. Just use this one because they've been validated.
For 360-degree videos?
Huh?
For 360-degree videos?
For the video, at least.
Okay.
But at the moment you do that for viewport, I think it's a fair it's a fair way to proceed, because this is more or less what you get in the viewport. Right? So my understanding is that also you take into account what you get in this viewport, so the parameters related to that viewport, and if you are getting access to that, which is also kind of demanding in terms of implementation, you have access to that. It's good to exploit this value. So you know already how to do that. So the rest is just applying the model that has been but that's just for meaningfulness, right? We said I want to do meaningful stuff, so do not try to print new stuff. You have good reflex, you have a good practice, but you can just improve on that front. So just do it better and expand also the thing. So, so it's about the transferability of your work, and that has been discussed already. And I see time running, but still, we said, okay, yes, you are doing, is it the right topic, view prediction, trajectory, and some people in the committee already asked you about, we could do that for rendering, low latency. So I think you have piece of work here that are easily transferable to this type of scenario. Not because you don't have all the technical implementation to do that, but still, for instance, in the first part of your work, if I want to use this for efficient rendering, can I use part of your work to do that? What would be required to do that?
I think you would need some data sets of people watching this kind of content with the gaze, because I think the gaze plays an important. I mean, if we're talking about rendering, we're talking mostly about very low latency gaze, foveal rendering, things like this. So some of the data sets that we use actually have both head and gaze movements, so we could do gaze predictions. And this could be
these are trajectories also, right?
Yes.
This is not head trajectory, but these are trajectories.
Yes.
This could be helpful here, and things that you have developed your model with the right data set, we can retrain the stuff, and
we could see we can definitely do it, but then I don't know how well it would go.
Yeah, but it's worth to be studied. So there is this. As you know what is transfer learning and this thing, that the models that you are proposing offer this also. If you have the right data set, the right use case, we can use it. Are you convinced that you can get something with that? So this is one of the models. There is also the things that are proposed in the second part. Okay.
Yeah, I think this would be very interesting. This just also that for example, eye movements is even more high, even more noisy. High frequency, so detection will be even more difficult. But yeah, we can do it.
Okay. For sake of time, let's go to bit ethics. Let me help you a little bit for the emotion part, right? Because I'm sure, and because Lucile and you are aware about AI Act and everything, and so you know that emotion is kind of and the AI Act is on the grid, right? Should we work on emotion? Should we use AI for emotion? And so, but maybe you can come back on your model, and I think that's
yes.
Yeah. When you propose this, I think what is interesting here is that you talk about federated learning and everything. What is interesting here is actually is it testing really or inferring? You said present when training, but absent when testing, when inferring, when using the model, right?
Yes.
Yes.
Yes. Yes. Deploying, testing.
So we have a model that done something which is mostly related to the content, and we don't have any. We are not monitoring user emotion in this.
What's your question?
When you do this type of model in deployment, are not looking at the emotion. We don't really need that, right?
If we are able to learn a model that learns transferable representations, yes. Yes, so the objective is to.
And that's a way to do it, right? And to protect also the citizens from using exploiting. When we go to the very first part of your work, so I think just to be clear, this way to proceed with AI and including emotion and so on, this is something which is, how to say, ethically correct in deployment. Okay? Because you don't actually, it's not about federated learning. It's not, you don't record anything about emotion of the people in usage, just something which is mostly related to the content. As for the first part also, most of the things come from the content. You characterize the content. This is a way also to deploy. You say, okay, there are some contents which are more prone to exhibit different behavior between the users, and some which are more, let's say, that will trigger a strong agreement in the deployment users and that. So we don't need to monitor. But still, it's kind of controversial, right? When you are studying this head motion and so on, it's kind of privacy. Biometric data. You have seen Vision Pro from Apple, the gaze, the raw gaze tracking, we don't have access to that. And this is stated on their product page, right? They advertise because they consider it's too sensitive, too personal data. So head trajectory could be also too personal.
Yeah.
So what do you think about that? Should we?
I mean, that's also what we do. The model, I mean, we've talked about where the prediction would be. Would it be on the user, end user side, on the server? So if we do the prediction on the client side, it would use the head trajectories, but the head trajectories would not be necessarily sent to a server. So I think the privacy in this way would be preserved. The only privacy we don't have is for the users that have participated in the experiments.
Developing the models that you have developed with the use case that you think, the scenarios that you think, and I'm not doubting about your intention, right? It's okay, but most of the things that you are doing, and when we are working on that, could be used to classify the behavior of people. That was touched by one. Okay, so you are developing some kind of research that if you put that and you stop it, you share at maximum. If it's in the hands of other people, then they can start to classify behavior with your work.
Yes, I mean, we don't do classification, we do prediction.
No, you didn't do it, but it won't be that difficult.
You could replace some part to add a classifier and something, but it's, I mean, it's always about the data. If you have access to the data of people, of course, you're going to be able to do this kind of thing, but then we use the data that is in the public data sets. So, I mean, this concern, to me, it's not really about the model, but more the access to the data.
Yeah, you demonstrate with the model that you can, and if you have some data, you are almost able to classify the behavior of people. And that could be a misusage according, depends on your, this stuff. I did not mention one in your sermon. Ethical reflection. I'm just inviting you to think about that, because, and I know it's difficult, and I'm facing the same things. We are developing stuff, and if you put that on the end of other people, and if they have the data, and if they are, we are offering them the possibility to do that. Meaningful. So I want to do something meaningful for the society. That's where I want to think about that for the. We are all facing this problem.
Yeah.
You are not the only one, but just think about it.
Do you want me to say?
You can say, no, it's just.
No, I agree. It's important to consider these things. And then, I mean, but it's easy to say this for many things that we develop, that they can be used. I mean, there is always the way we think how this will be used, and then there is always some usage that can be made that does not really follow what we thought it was going to be. And then this is a risk we have to keep in mind. But yeah. This is a difficult question, as you said.
Our scientific envy and the knowledge quest, the quest for knowledge. Let's not forget about. But it's just an invitation. You don't take it too. We are all facing this problem. The people from this committee, we can discuss.
Yeah, I accept the invitation.
Yeah, it's just because you are enthusiastic, you are really engaged in your work. And sometimes when you're following these things in a virtuous manner, let's not forget that. Voilà. It's a great work. I'm very pleased to have been here. Thanks for the discussion together. And now I hand over to Lucile.
So thank you, Patrick. So I will be quick. I won't ask any question. Just want to say a few words about content, the thesis. So first, thank you for the very efficient presentation. I think it reflects the quality of the presentation that you could produce along the thesis. And I want to say also that content has been very hardworking, enthusiastic, reliable, and rigorous, even in times of lockdown, because we've been in lockdown for several months at the beginning of the thesis, and even also under regular teaching load, that it is important to mention. You have been, I think, imaginative. So DVMS is your proposal to have new solutions. And you've also shown something which is, I think, important, is that you've shown the capability to work with other people. So you've spent 1 month in Firenze. That, I mean, 3 months is working with them closely, but being present in person, and that gave rise to the analysis paper. Then you've spent 1 month in Firenze, 3 months is in CWI. This is still work in progress now with Remy on these aspects of using condition models. You've been also always at the crossroad of computer vision and VR, HCI, and this is, as Patrick emphasized, something which is important to mention, because it is to be negotiated very carefully, and it's quite challenging, but still very exciting also. And you've been able to really produce new relevant models and to invent solutions. You've been also very enthusiastic in actually producing, and very rigorous also in producing thorough data analysis to properly motivate the directions, which is very important. And you've shown also a lot of enthusiasm and will to share your tools, the tools that you've produced, and you've really handled that with constant rigor in formatting data and code, which is very appreciable. So yes, it has been really a true intellectual and a human pleasure to work with you for these last 3 years. And I thank you, and I sincerely wish you the best for the future. Thank you. Thank you.
Merci beaucoup. Thank you very much. Alors, il y a des questions dans la salle. N'en a-t-il? Et s'ils ont pas de questions,
il y en a un.
Il y en a un.
Abstiendrait de toute question.
Depuis une semaine.
Donc, s'ils veulent poser une question, ils peuvent le faire. Si vous sautez à chaque. Une question? C'est vrai?
On aura le temps à discuter après.
C'est toujours bien de poser une question. Il n'y en a pas.
Il n'y en a pas.
Il n'y en a pas. Il n'y en a pas. Eh bien, donc, c'est sûr. Ça lui ferait plaisir.
Non, non, c'est bon là.
Je suis pas sûr.
Non, c'est bon.
Il n'est pas fatigué.
Il n'est pas fatigué. Bon, bah écoute, Quentin, donc voilà, on va délibérer. Maintenant.
Ouais, tu coupes le live YouTube.
Comment ça se passe? Nous, on reste ici.
On reste ici.
Donc, ça veut dire qu'on vous demande de partir. Ne partez pas trop loin. Ça va essayer d'être rapide et très bien que vous revenez quand même. J'annonce un peu le résultat. On va essayer d'être plus rapide à la déclaration que.
Je coupe le live YouTube et je remets.
Là, le live tournait dans le temps et là, il reprend.
On se coupe. On voit.
On prend de la caméra. Il y a la télécommande, vous pouvez régler là.
Ouais, ok.
Comme on voit aussi. Est-ce que le live va bien recommencer? Quelqu'un peut regarder ou pas?
Oui, je suis dessus là.
Il y a de la latence.
Oui, on est à côté de moi, mais.
Ok.
Attends.
Ouais, j'aurais dû mettre en low latency, mais pas.
Non, parce que les gens qui veulent venir, on peut fermer. De toute façon,
Ouais,
là, c'est public. Hein,
Ouais.
Alors, ça y est, tout le monde est prêt? Ok, alors, je vais le faire en français, parce que c'est un document français qu'on va éditer, mais on s'est bien mis d'accord avec tous les membres du jury qui comprennent le français en plus. Donc, voilà. Donc j'ai Quentin. Donc, d'abord, on a trouvé que tu avais exposé ton travail de manière fluide et dynamique, et ça, on a bien apprécié ça. que tu avais bien conçu ta présentation, qu'elle était très bien illustrée et que tu as réussi à mettre en évidence toute la richesse de ton travail et résumé un manuscrit qui était ample et dense. Bravo pour ça. On a unanimement salué un travail substantiel sur un sujet difficile, très ouvert parce qu'il fait appel à plusieurs disciplines. On a apprécié ta connaissance profonde des travaux de l'état de l'art, notamment sur l'aspect computer vision. On a trouvé que tu avais défini des objectifs clairs, tu avais bien défini ton cadre de travail et tu as mené après un travail rigoureux autour de ces objectifs, que tu as atteint des contributions scientifiques qui sont originales, de grande qualité, qui ont été diffusées dans des tribunes pertinentes, déjà saluées par la communauté. On a apprécié au fait aussi que tu sois en fait un pont entre des disciplines, celle de la vision par ordinateur, computer vision, et celle des communications visuelles, notamment sur l'aspect réseau, aussi sur les communautés QoI qualité. Voilà, des contributions excellentes. Tu as aussi des nouvelles, tu as été créatif. Donc, ça, c'est aussi, tu as des idées et elles sont bonnes, tu as des bonnes intuitions et on salue ça. On salue aussi tes talents d'expérimentateur, à la fois en simulation, mais aussi avec l'expérimentation avec les humains, psychophysique. Et ça demande une rigueur scientifique. Et sur les deux domaines, et c'est pas facile, tu l'as fait et tu l'as fait avec grande application. Donc, félicitations aussi pour ça. On salue aussi un chercheur, c'est quelqu'un qui doit pouvoir collaborer dans son équipe, mais aussi au-delà. Et on voit bien que tout ce travail compliqué que tu as pu faire en développant des collaborations à l'international, en allant travailler avec d'autres chercheurs, et on salue ça aussi. Et on salue évidemment tout l'aspect, l'attention que tu as posée à rendre tes résultats reproductibles. Et ça, c'est aussi une grande vertu. Alors, on t'a un peu, c'est un travail de qualité comme ça, aussi profond et dense. On t'a bien cuisiné sur les questions. Donc, on a eu une session longue, intense, vivante. On espère que tu as apprécié un peu ce moment, quand même. On a trouvé que tu étais convaincant dans tes réponses. On a apprécié aussi le niveau de précaution que tu mettais dans tes réponses. C'est-à-dire, savoir dire non, là, à un moment, ça, c'est pas mon domaine et j'aurais pu faire autrement. Donc ça, on a vraiment apprécié ce côté précaution scientifique et c'est très bien d'avoir cette humilité appropriée dans l'appréciation et la prise de recul de ces résultats. Évidemment, cette session aussi, elle a montré aussi, elle couvrait beaucoup de domaines parce que tu avais un jury pluridisciplinaire, on ne vient pas tous des mêmes communautés, tu as les informaticiens, tu as ceux qui viennent de la communication, des sciences de la communication, il y a ceux qui viennent du traitement de signal, et tu as affronté ça avec courage et avec application. Donc, merci pour ça. On a apprécié aussi qu'en fait, tu vois, ça nous a permis de discuter de l'aspect technique dans les questions, mais aussi d'aborder des aspects aussi qui sont l'impact de tes travaux en termes sociétal et éthique. Et ça nous a permis d'aller aussi sur ces terrains-là. Et c'était très intéressant. Tu nous as montré toute la maîtrise que tu as sur ton travail technique, scientifique, ton recul. Tu nous as montré une excellente maturité scientifique. Voilà, et tu as une bonne vision sur la suite des travaux à mener. Et voilà, il y a des défis pour ta communauté. Donc, pour toutes ces raisons, tu comprendras qu'on est très heureux de te délivrer le titre de docteur en informatique de l'université. Alors, je ne veux pas que je me trompe parce que l'université Côte d'Azur. Voilà, et c'est vraiment mérité. À titre personnel, à qu'on fasse la clap, moi je suis vraiment honoré d'avoir présidé le jury, d'abord parce que par rapport à toutes les personnes qui étaient là, j'étais rencontré à ta première conférence et j'avais été déjà impressionné. Tu avais eu le Best Paper Award ACM MMM6, je n'étais pas dans le comité, si j'avais eu à donner le Best Paper Award, ça aurait été toi, et je ne te connaissais pas. Voilà. Donc, j'étais absolument réjoui de participer. Quand j'étais invité à participer au jury, d'y participer, on t'a cuisiné parce que tu le méritais bien, parce que ça fait partie du passage. Et vraiment, franchement, félicitations. Je pense que tu incarnes ce qu'on attend d'un jeune scientifique qui s'engage dans la recherche avec envie, passion, avec rigueur. On a parlé du sarment. Je ne sais pas si tu vas le lire, mais voilà, je pense que je suis très fier qu'on produise, que des jeunes comme toi s'emparent de domaine et que ça vienne aussi un peu de la France, je le dis. Donc, merci pour ça. Voilà, et encore bravo.
Lire le serment.
Alors,
Choisis de lire le serment.
tu peux dire un petit mot, mais est-ce que tu veux lire le serment?
Non,
mais je l'avais préparé. Voilà, donc tu souhaites prêter serment?
Je souhaite prêter serment.
Eh bien, voilà.
En français. Je vais le faire en français. En présence de mes pairs, parvenu à l'issue de mon doctorat en informatique et ayant ainsi pratiqué, dans ma quête du savoir, l'exercice d'une recherche scientifique exigeante, en cultivant la rigueur intellectuelle, la réflexivité éthique et dans le respect des principes de l'intégrité scientifique, je m'engage, pour ce qui dépendra de moi, dans la suite de ma carrière professionnelle, quel qu'en soit le secteur ou le domaine d'activité, à maintenir une conduite intègre dans mon rapport du savoir, mes méthodes et mes résultats. Et j'ai pas préparé de slide pour remercier, parce que j'ai passé déjà beaucoup trop de temps sur cette présentation-là. Mais merci beaucoup. Non, je fais pas en anglais. Ah, non, je vais faire moitié français, moitié anglais. Donc, merci beaucoup à toutes les personnes qui sont ici et à distance. Thank you to the jury. It was really an honor to defend in front of really experts of the domain, and especially the reviewers who took a lot of time to read the long thesis and make a feedback in such a short time that we have for reviewing in France. Thank you to all the people I have been working with. So here I can cite Rémi, Florent, Franz, Hugo, as well as Hélène, Marco in Florence as well. Lorenzo, Francesco, Federico, Alberto in Amsterdam as well. Thank you to Sylvia, Irene, Pablo. Thank you to all the people who have made this journey more pleasable, that I can now call friends. So again, the people here, the people in Amsterdam as well, I cannot name everyone for this. I would probably forget at least one name. So thank you to everyone here and remote, to all the friends. I had really a great time here, and I'm sad to go somewhere else, but I will definitely come back, and we will see each other again. And finally, thank you to Lucile. I think there were a lot of compliments and for me, and also many things I did, and I am here. It's thanks to Lucile. She was always guiding me right. She always knows everything. She's this is in this, yeah.
En français?
Non, mais c'est difficile dans les deux cas. de langue. Mais je sais pas ce que je veux dire, mais oui, merci beaucoup à Lucile qui disait que je suis enthousiaste. Je pense que ça jouait aussi un grand rôle que Lucile réussisse toujours à me guider, à me motiver, à remettre dans le contexte, et ça merci beaucoup. C'était vraiment, je pense, super important pour la réussite de cette thèse, et merci.
T'es bien là?
On va continuer. Hein.
Ouais.
Il n'y a pas encore des questions là, non?
Et bien bravo.
Photo avec ton jury.
Ah oui, on peut faire une photo.
Ouais.
Comment ça fonctionne?
Bah, on se met.
Bah là, on va se mettre là, tu vois. Et puis il y a des gens qui vont venir en photo, et puis voilà.
Ok.
Mais moi.
Tu auras tout ton comité. aider. Qui c'est qui nous prend photo?
Congratulations from my side as well.
So
Thank you very much,
Well done.
Gabriel.
Hi,
We are
everyone.
just taking a picture with you.
Yeah, you cannot see us, but we are back to the
Okay.
TV.
Yeah, I should remove my coat.
bon, alors nous on est grands. Et on...
On met un peu plus près.
Il valide la qualité.
C'est bon.
On va calculer le SSIM.
Thank you very much to the committee. Thank you, Laura, Gabriel, Gwendal, Aljosa, and we hope to see you in person sometime in the near future. Thank you again for the examination.
Thank you.
We miss you.
You're welcome.
Bye bye.
Thank you,
Bye.
and
Bye.
especially with the
Thank you.
French cuisine, so think about that.
Yeah. Thank you so much. Goodbye.
Bye bye.
Bye.
Carole. Bon, voilà. Il n'y a pas de pou là?
Alors, on va manger et après on commencera.
Tu as mon billet.
Voilà, tu peux le
C'est pas le même.
Non, là, il faut.
Je te le transfère après. Ouais, tu as le